Think about the night sky for a moment. You look up and see countless pinpricks of light scattered across the darkness. For thousands of years, humans believed this glowing tapestry was the universe, complete and knowable. We counted the stars, mapped their movements, and felt we understood the cosmos. But reality, it turns out, isn't nearly that simple. The universe has been keeping secrets from us, hiding its true nature behind a dazzling display of starlight. What we see when we look up isn't the main story at all. It's barely even a footnote. Most of what exists around us, holding galaxies together and shaping the very structure of space itself, is completely invisible to our eyes. Scientists have discovered that the brilliant stars and glowing gas clouds that captivate us represent only about 5% of everything that exists. The rest is hidden, dark, mysterious, and yet it controls almost everything about how the universe works. We'll explore this invisible majority in this video and discover just how much we still don't know about the cosmos we call home. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now let's get started. The night sky above us holds secrets that stretch back billions of years, long before telescopes were invented, long before anyone used words like physics or astronomy. When ancient peoples looked up at the stars, they saw patterns, stories, gods dancing across the darkness. What they couldn't see, what nobody could see, until very recently, was that the darkness itself might be the most important part of the story. Scientists today face a puzzle that sounds almost like magic. The universe, it turns out, is mostly made of something we can't see, can't touch, can detect with any normal instrument. This invisible substance has a name that sounds like it belongs in a fantasy novel: dark matter. But there's nothing fictional about it. The evidence suggests that everything we can observe, every star, every planet, every grain of cosmic dust, represents less than 1/6 of all the matter that exists. Think about that for a moment. You, your house, the Earth, the Sun, all the billions of stars in our galaxy, they're all part of the tiny minority. The rest of the universe consists of this mysterious, invisible material that doesn't glow, doesn't absorb light, doesn't seem to interact with ordinary matter in any way we can easily measure. Yet without it, galaxies wouldn't exist, stars wouldn't have formed, and we wouldn't be here to wonder about any of this. The story begins with galaxies spinning in space. These massive collections of stars, some containing hundreds of billions of suns, rotate like enormous cosmic pinwheels. When astronomers measure how fast the stars move, especially the ones at the outer edges of galaxies, something doesn't add up. The math says these outer stars should be moving much more slowly than they actually are. If you add up all the visible matter in a galaxy, all the stars you can count, all the gas and dust you can detect, there simply isn't enough gravity to keep the galaxy spinning at the observed speed. It's like watching a figure skater spin with their arms extended, but spinning far faster than physics should allow. The only way to make sense of it is if there's additional mass you can't see, providing extra gravitational pull. In the case of galaxies, that extra mass has to be enormous, several times more massive than all the visible stars combined. This discovery emerged gradually through the 20th century. In the early decades, astronomers studying clusters of galaxies noticed that individual galaxies moved too quickly within their clusters. The visible matter in all those galaxies combined couldn't provide enough gravity to hold the cluster together. Later, in the 1970s, astronomer Vera Rubin made detailed measurements of individual galaxy rotation. Her careful observations confirmed what others had suspected. Galaxies contain far more matter than meets the eye. The implications are staggering. Every galaxy we can observe appears to be embedded in a vast halo of invisible material. This dark matter, as scientists call it, doesn't emit light, doesn't reflect light, doesn't absorb light. Light passes right through it, as if it weren't there. The only way we know it exists is through its gravitational effects on the things we can see. Picture the Milky Way, our home galaxy, as a glowing spiral of stars against the cosmic darkness. What we actually see is just the bright decoration on a much larger, invisible structure. The dark matter halo surrounding our galaxy extends far beyond the visible edge, perhaps 2 or 3 times farther than the most distant stars we can detect. We're living inside this invisible ocean without even noticing it. The mystery deepens when you consider what dark matter might actually be. Scientists have proposed various candidates over the decades. Maybe it's made of exotic particles that barely interact with ordinary matter. These hypothetical particles would be created in high-energy physics experiments or detected in deep underground laboratories designed to catch them as they pass through the Earth. So far, despite decades of searching, no one has definitively detected such particles. Another possibility involves objects made of ordinary matter that simply don't shine. Brown dwarfs, which are failed stars too small to ignite nuclear fusion, ancient white dwarf stars that have cooled until they're nearly invisible. Primordial black holes formed in the early universe. Free-floating planets ejected from their solar systems. Astronomers have searched for these objects and found some, but nowhere near enough to account for all the missing mass. Some scientists wonder whether the problem lies not with invisible matter, but with our understanding of gravity itself. Perhaps gravity behaves differently on cosmic scales than it does in our solar system. Modified theories of gravity attempt to explain galaxy rotation without invoking dark matter. These ideas remain controversial, partly because they struggle to explain other observations that dark matter handles naturally. The cosmic web provides another compelling piece of evidence. When astronomers map the large-scale structure of the universe, they find that galaxies aren't randomly scattered through space. Instead, they're arranged in an intricate pattern of filaments and voids, like a 3-dimensional spiderweb stretching across billions of light years. Computer simulations of how the universe evolved can reproduce this pattern, but only if they include large amounts of dark matter. The invisible material provides the gravitational scaffolding on which visible matter assembles into the structures we observe today. This scaffolding began forming very early in cosmic history, when the universe was still young and hot. Tiny fluctuations in the density of dark matter, present just a few 100,000 years after the Big Bang, grew under their own gravity. Over millions of years, these fluctuations became the seeds around which the first galaxies formed. Without dark matter, the universe would be a much emptier, more uniform place. The philosophical implications are profound. We live in a cosmos where the fundamental building blocks of reality remain hidden from our senses. Everything we can perceive directly represents just a small fraction of what actually exists. It's humbling to realize that our most basic inventory of the universe was so incomplete. For centuries, humans assumed that what we could see was essentially everything that mattered. Stars, planets, gas, dust. These seemed to be the primary constituents of cosmic architecture. Now we understand that the visible universe is more like the foam on top of an ocean. The foam is beautiful, complex, full of interesting patterns and structures, but the vast bulk of the ocean lies beneath, invisible from the surface. This hidden majority doesn't just passively fill space, it actively shapes the evolution of everything we can observe. Dark matter determines where galaxies form, how they evolve, where stars are born, where planets can exist. Current research efforts span the globe. Deep underground detectors wait patiently for dark matter particles to reveal themselves. Particle accelerators smash protons together at enormous energies, hoping to create dark matter in the laboratory. Space-based telescopes map the distribution of matter throughout the universe, using gravitational lensing, a technique that reveals how dark matter bends light from distant galaxies. Each approach offers a different window into the mystery. Underground detectors could catch dark matter particles directly, providing the first definitive proof of what this invisible material actually is. Particle accelerators might create dark matter artificially, allowing scientists to study its properties in controlled conditions. Astronomical observations continue to refine our maps of where dark matter exists and how it behaves on cosmic scales. The search continues because the stakes are so high. Understanding dark matter would revolutionize our picture of physical reality. It might reveal new fundamental particles, new forces of nature, new principles governing the behavior of matter and energy. Or it might point toward a completely different understanding of space, time, and gravity. Either way, solving the dark matter puzzle would rank among the greatest scientific discoveries in human history. Until then, we're left to contemplate the strangeness of our situation. You're sitting in a room, perhaps looking out a window at the night sky, surrounded by an invisible presence that outweighs everything you can see by more than 5 to 1. This presence doesn't announce itself, doesn't interact with you in any obvious way, yet without it, none of the cosmic structures that led to your existence would have formed. The stars that created the heavy elements in your body, the galaxy that houses our solar system, the gravitational processes that assembled planets from cosmic dust, all of these depend on the invisible foundation that dark matter provides. It's a reminder that reality often exceeds our imagination. The universe turns out to be stranger, more subtle, more layered than our ancestors could have conceived. What appears to be empty space teems with invisible activity. What seems solid and permanent floats in seas of mystery. The boundary between the known and unknown passes right through our most basic questions about existence itself. When we think about everything around us, it's strange to realize that most of reality remains completely invisible. The universe operates on a principle that challenges our deepest assumptions about what exists. We trust our eyes, naturally, because sight guides us through daily life. But when it comes to the cosmos, vision becomes an unreliable narrator. Consider how galaxies behave, spinning through space with a kind of stubborn defiance. If you calculate the mass of all the stars, all the glowing gas clouds, all the cosmic dust that telescopes can detect, something doesn't add up. These galaxies should be flying apart, their outer stars drifting away like loose marbles rolling off a spinning table. The visible matter simply isn't heavy enough to hold things together with its gravitational grip. But galaxies don't fall apart. They maintain their structure, their spiral arms sweeping elegantly through space, their outer regions rotating at speeds that seem impossible, given what we can see. This observation forces us into an uncomfortable conclusion that most of what exists beyond our perception. The mathematics are surprisingly straightforward. Stars close to a galaxy's center should orbit quickly, pulled by the concentrated mass at the core. Stars farther out should move more slowly, just like planets in our solar system. Mercury sits around the Sun in 88 days, while distant Neptune takes 165 years to complete a single journey. This makes intuitive sense. Gravity weakens with distance. Galaxies, however, refuse to follow this script. Their outer stars maintain the same orbital speeds as inner stars, as if some invisible hand were guiding them. The only explanation that fits the observations involves vast halos of unseen matter, extending far beyond the glowing regions we photograph. These halos contain most of the galaxy's actual mass, creating gravitational wells deep enough to prevent stellar escape. This invisible component has earned the name dark matter, though the term reveals more about our ignorance than our knowledge. It's dark because it doesn't emit, absorb, or reflect light. It's matter because it has mass, exerting gravitational influence on everything around it. Beyond these two simple facts, mystery takes over. Think about the philosophical implications for a moment. We live in a universe where the majority of reality operates in complete silence, shaping everything while revealing nothing about itself. It's like discovering that most of a symphony plays at frequencies beyond human hearing. We catch only fragments of the full composition. Scientists estimate that ordinary matter, the atoms that build stars and planets and people, accounts for roughly 5% of the universe's total contents. 5%, everything we've ever seen, measured, or touched, represents a tiny minority of what actually exists. The night sky, magnificent as it appears, shows us only the visible decoration on a much grander, hidden architecture. This realization emerged gradually during the 20th century, as astronomers developed better tools for measuring cosmic motions. Each new observation strengthened the case for invisible mass. Computer simulations became particularly revealing. When researchers tried to model the universe's evolution using only visible matter, the results looked nothing like the real cosmos, but add the unseen component, and suddenly virtual galaxies formed exactly where real ones appeared. The search for this hidden reality has spawned an entire scientific enterprise. Underground laboratories burrow deep beneath mountains, shielding sensitive detectors from cosmic interference. Particle accelerators smash protons together at nearly light speed, hoping to create dark matter particles in fleeting collisions. Space telescopes map how invisible mass bends and distorts the light from distant galaxies, creating gravitational lenses that reveal the presence of what cannot be seen directly. All of this effort chases something that has never announced itself openly. Dark matter remains stubbornly indirect, known only through its gravitational fingerprints. It's like hearing music from another room, knowing someone must be playing, even though the door stays closed. The evidence accumulates from every direction. Galaxy clusters, the largest structures in the universe, hold together only if dark matter provides the necessary gravitational glue. The cosmic web, that vast network of filaments connecting distant regions, makes sense only when invisible matter guides its formation. Even the cosmic microwave background, the afterglow of the early universe, carries patterns that match predictions involving dark matter. Perhaps there's something oddly comforting about acknowledging such profound mystery. Science often works this way, identifying what must exist before understanding what it actually is. The periodic table had gaps long before the missing elements were discovered. Neptune's existence was calculated before anyone saw it through a telescope. Sometimes the most important discoveries begin not with seeing, but with recognizing what the visible evidence demands must be there. The hunt for dark matter continues, driven by questions rather than answers. What kind of particles could interact gravitationally, but remain otherwise invisible? How do they clump together to form those massive halos? When did they first influence cosmic evolution? These questions guide researchers through increasingly sophisticated experiments, each designed to catch a glimpse of the universe's hidden majority. Meanwhile, the philosophical weight of dark matter settles over our understanding of existence itself. We inhabit a cosmos where most of reality operates according to rules we haven't deciphered, composed of substances we can't identify, following patterns we're only beginning to trace. It's humbling to realize that despite centuries of scientific progress, the universe still keeps most of its secrets. Yet this ignorance doesn't feel paralyzing. Instead, it opens up vast territories for exploration, infinite puzzles waiting to be solved. The invisible universe surrounds us, shapes us, makes our existence possible, all while maintaining perfect silence. Every galaxy we photograph, every star we study, every planet we discover, owes its existence to this hidden foundation. Most of what exists cannot be seen. This idea sounds almost mystical, but it emerges from careful measurement, from decades of astronomers pointing instruments at the sky and finding again and again that the universe weighs more than it appears to weigh. When we talk about the cosmos, we often picture glowing stars, swirling galaxies, bright nebulae painted in colors that make us pause in wonder. These luminous objects feel like the main characters of the cosmic story, but they represent only about 5% of everything that exists. 5%. The rest remains invisible to our eyes, to our cameras, to every form of light we know how to detect. This invisible majority divides into two mysterious categories. Roughly 27% is something called dark matter. 68% is even stranger, something called dark energy that appears to be pushing the universe apart faster and faster as time goes on. But dark energy deserves its own conversation. For now, the focus is on that hidden 27%. The dark matter that surrounds us, fills the space between galaxies, and shapes the very structure of reality. The natural question is simple. How can we claim to know about something we cannot see? Now, the answer reveals something profound about how science actually works. We do not rely only on vision. We measure by inference, by studying the consequences, by examining the footprints left behind on the things we can observe. Light bends when it travels near massive objects. Einstein predicted this behavior in his theory of general relativity, and astronomers have confirmed it countless times since then. By mapping how light from distant galaxies gets distorted as it travels toward us, scientists can create maps of invisible matter. They find vast regions where no stars shine, yet where gravity bends light just the same. These invisible clumps and filaments form the large-scale structure of the universe. They act like scaffolding beneath a building, guiding where galaxies form, where clusters of galaxies gather, how the cosmic web stretches across billions of light years. The visible universe, beautiful as it is, rests on this hidden framework. Sometimes the evidence becomes dramatic. Consider something called the bullet cluster, where two enormous groups of galaxies collided with each other. Astronomers can observe the hot gas from this collision, using X-rays and visible light. But here is the strange part. The gas, which should contain most of the mass, lingers in one region after the collision. Meanwhile, gravitational lensing shows that most of the actual mass lies elsewhere, separated from the gas. This mismatch demonstrates that something other than normal matter must be present, carrying most of the gravitational weight. The bullet cluster stands as one of the clearest visual proofs that dark matter exists. Even though we cannot see dark matter directly, the invisible universe extends much closer to home as well. Within our own Milky Way galaxy, the way stars move and distribute themselves suggests an enormous invisible halo. This halo contains roughly 10 times more mass than all the visible matter in our galaxy combined. It stretches far beyond the disk of stars we see when we look up at the night sky, wrapping our galaxy in a spherical cloak of unseen mass. We move through this dark matter constantly, yet we have no direct sensation of it. It does not push against us, does not block sunlight, does not interact with atoms in ways our senses can detect. But its gravitational influence shapes everything around us. Our entire solar system exists as just a tiny speck within this vast halo, like a small bubble suspended in an invisible ocean. Living in such a universe requires accepting a humbling truth. What we can see is not what dominates reality. We exist in the minority slice of existence, the part that glows and can be comprehended through direct observation, while the bulk of reality remains hidden from view. This does not make the visible universe unimportant. After all, it gave rise to life, to conscious minds that can wonder about their place in the cosmos, to the technology that allows us to probe deeper into these mysteries. But the visible universe tells only part of the story. It represents the bright fringe of a much larger, much stranger tapestry. The distinction between seen and unseen also changes how we think about knowledge itself. For centuries, humans have equated knowledge with sight. We say things like, "I see," when we mean, "I understand." Seeing has been believing. Yet, modern cosmology reveals that understanding often comes not from direct observation, but from careful deduction. The invisible may be more fundamental than the visible. We find ourselves forced to acknowledge that sight is not the ultimate authority when it comes to truth. Gravity, the motions of galaxies, the bending of light. These phenomena reveal aspects of reality that vision alone cannot capture. This shift has practical consequences for how we study the universe. Modern observatories do not simply capture visible light. They record X-rays, gamma rays, radio waves, microwaves, all different forms of electromagnetic radiation that carry different kinds of information about cosmic processes. Even so, all these forms of light together still fail to directly detect dark matter. Dark matter remains outside the entire electromagnetic spectrum, interacting with ordinary matter only through gravity, and perhaps through other forces we have not yet learned to observe. This raises deeper questions. What is this unseen mass actually made of? If it consists of something other than atoms, what could that something be? Theories abound, from exotic particles predicted by extensions of our current understanding of physics, to primordial black holes that might have formed in the very early universe. Each possibility comes with its own challenges, its own predictions, its own puzzles. None has been definitively confirmed yet. But before wandering too far into those theoretical possibilities, It feels worth pausing on the simple, almost overwhelming fact of how little we actually see. When you look up at the night sky, you are observing that 5%, the luminous minority of existence, the shining islands of stars are like lanterns strung across a vast invisible framework. The glow is real, the beauty undeniable, but it all rests upon a hidden foundation that we can only infer exists. Without that invisible foundation, the lights would not be where they are, the galaxies would not have formed in the patterns we observe, the cosmic web would not stretch across space in the intricate structure that astronomers map. There is something oddly comforting about knowing we are suspended within something larger, something unseen, yet, apparently, dependable. It suggests the universe is far more mysterious than casual observation would indicate, but also more stable. Galaxies are held in their positions, stars remain bound in their clusters, the entire cosmic web maintains its structure across billions of light years, all because of a presence we cannot see but can confidently infer. When we think about weight in everyday experience, we imagine something tangible. A heavy bag of groceries, a suitcase that makes your shoulder ache, the reassuring pull of gravity when you settle into a comfortable chair. Weight belongs to objects we can hold, touch, place on a scale. It presses downward, makes its presence unmistakably known. In daily life, weight connects directly to matter we can see and handle. But in the broader universe, weight takes on a much more expansive meaning. Gravity responds to all mass, whether visible or invisible. In this sense, the cosmos reveals a truth that challenges our everyday intuitions. The universe is significantly heavier than it appears to be. Astronomers discovered this not through accident, but through patient, careful observation. They studied how galaxies rotate, how clusters of galaxies move relative to each other, how light bends during its journey across vast distances. Measurement after measurement revealed the same basic story. There is substantially more mass present than what meets the eye. To appreciate the scale of this discrepancy, imagine adding up every star in the Milky Way galaxy. There are perhaps 400 billion of them, each contributing its mass to the total. Now, include all the glowing gas clouds, all the streams of cosmic dust, every atom of ordinary matter we can detect through any form of light or radiation. The space between stars isn't truly empty, though we often think of it that way. Vast clouds of hydrogen and helium stretch across light years, mixed with cosmic dust that dims the light from distant suns. Black holes lurk within the remnants of dead stars, invisible but undeniably real. When astronomers add up all this material, all the stuff they can actually detect and measure, they get a number that should define our galaxy's total mass. But here's where things get strange. The gravity holding the Milky Way together tells a completely different story. The actual gravitational pull suggests there's 10 times more matter than what we can see. 10 times more. This isn't a small error in calculation, or a few missed stars hiding behind dust clouds. We're talking about a discrepancy so massive it changes everything we thought we knew about our cosmic neighborhood. The invisible matter doesn't just slightly outweigh the visible, it dominates completely. Everything we can see, every star, every planet, every glowing gas cloud, becomes almost decorative compared to this vast, unseen presence that surrounds us. It's like discovering that the foundation of your house is 10 times larger than the house itself, extending deep underground where you never noticed it. This same pattern shows up everywhere astronomers look. Galaxy clusters, some of the most massive structures in the entire universe, reveal their hidden weight in dramatic ways. Galaxies within these clusters zip around at incredible speeds, far too fast for the visible matter alone to keep them bound together. Yet somehow, these clusters don't fly apart. Something invisible provides the gravitational glue that holds everything in place. Even the hot gas that fills the spaces between galaxies, glowing brightly in X-ray light, can't account for all the binding mass needed. Once again, the majority remains hidden from our instruments. It's as if the universe is playing an elaborate game of hide and seek, with most of the players completely invisible to us. One of the most beautiful demonstrations of this hidden weight comes through gravitational lensing. Einstein showed us that mass bends the fabric of space-time itself, and light has no choice but to follow those curves. When distant galaxies sit behind massive clusters, their light gets bent and twisted, creating these gorgeous arcs and multiple images scattered across the sky. By carefully measuring how much the light bends, astronomers can map exactly where the mass is located in these clusters. Time after time, these maps show concentrated mass in places where absolutely no glowing matter exists. The weight is there, measurable and undeniable, but completely invisible to every instrument we've built that depends on light. The word dark in dark matter can be misleading, suggesting something ominous or shadowy. In reality, dark simply means transparent to light. This mysterious substance doesn't glow like stars, doesn't absorb light like dust, doesn't scatter radiation like gas clouds. It passes through all electromagnetic interactions without leaving the slightest trace. Gravity remains its only calling card, but gravity has been more than enough to reveal its enormous influence. This invisible weight has shaped the entire history of our universe. Shortly after the Big Bang, ordinary matter and radiation were locked together in an incredibly dense, hot plasma. As space itself expanded and temperatures dropped, atoms finally formed and light broke free from matter, creating the cosmic microwave background radiation we can still detect today. The patterns in this ancient light, tiny temperature variations rippling across the entire sky, carry information about how mass was distributed in the early universe. When scientists analyze these patterns, they find that ordinary matter alone couldn't possibly have created the structures we see today. Without the extra gravitational pull of dark matter, galaxies simply wouldn't have formed quickly enough. The invisible weight acted like cosmic scaffolding, pulling ordinary matter into clumps and allowing the first stars and galaxies to ignite. Dark matter isn't just an extra ingredient sprinkled on top of the universe, it's absolutely essential to the cosmic story. Without it, space would remain a thin, uniform soup of particles. No galaxies would form, no stars would shine, no planets would coalesce, and no curious minds would exist to ponder these mysteries. Despite its fundamental importance, we still don't know what dark matter actually is. Scientists have proposed various candidates with exotic names like WIMPs, which stands for weakly interacting massive particles, or axions, or sterile neutrinos. Each candidate attempts to explain how something can have mass while remaining completely invisible to light. Deep underground laboratories house experiments searching for the faintest hint of interaction. Giant detectors, filled with noble gases, carefully shielded from cosmic rays, sit in perfect silence, waiting for the incredibly rare possibility that a dark matter particle might collide with an ordinary atom. So far, that silence continues, unbroken. This doesn't mean the search is hopeless, though. In science, persistence often pays off in unexpected ways. The invisible weight leaves its signature everywhere. In the rotation of galaxies, in the motion of clusters, in the patterns of ancient light. It cannot be ignored or explained away. Each new piece of evidence confirms that something massive exists beyond our ability to see it directly. The scale of this hidden reality can be difficult to comprehend. About 27% of the entire universe consists of dark matter. Ordinary matter, the stuff that makes stars and planets and people, accounts for less than 5% of everything that exists. For every kilogram of normal matter, there are more than 5 kilograms of invisible matter surrounding it. For every star that burns in the night sky, there's an enormous halo of unseen particles holding it in gravitational embrace. For every planet that orbits its sun, an ocean of invisible matter flows around it. The familiar world of light and substance that we call home turns out to be the exception, not the rule. There's something deeply humbling about this discovery. Human beings evolved in a universe of visible matter, learning to trust our senses and believe that what we see represents reality. But the cosmos reveals that the opposite is true. The majority of everything that exists remains invisible to us. The weight of the universe gets carried by something we cannot see, touch, or sense in any direct way. This knowledge changes how we might think about our place in existence. We are creatures of light living in a luminous world, yet we're supported by an invisible foundation that dwarfs everything we can perceive. Every galaxy, every star, every world owes its stability to the gravity of something completely unknown. Without this unseen presence, the universe would dissolve into formless chaos. It's as though the visible universe resembles delicate lace stretched over a strong but hidden frame. The lace catches our attention with its beauty and intricate patterns, but the frame gives it structure and meaning. When you feel gravity pulling you toward the earth beneath your feet, you're experiencing the same fundamental force that reveals the weight of the invisible throughout the cosmos. Gravity doesn't distinguish between matter that shines and matter that hides. It pulls on everything with perfect equality. The apple falls from the tree, our planet orbits the sun, and entire galaxies hold together, all following the same universal law that connects the smallest scales to the largest structures in existence. The cosmos holds secrets that challenge everything we thought we understood about reality. Isaac Newton gave us the laws that govern falling apples and orbiting planets. Albert Einstein refined those ideas with his theories of relativity. Yet, both of these brilliant minds would be puzzled by what we now know about the universe, because most of the mass that shapes everything around us remains completely hidden from view. Imagine for a moment if this invisible matter could suddenly become visible to our eyes. The night sky would transform into something almost unrecognizable. Stars would sit at the centers of vast, glowing halos that stretch far beyond what we currently see. Our own Milky Way galaxy wouldn't appear as that familiar band of light stretching across the darkness. Instead, it would look like an enormous, luminous sphere that surrounds us completely. Galaxy clusters scattered throughout space would shine like cosmic lanterns, each wrapped in faintly glowing cocoons of matter that dwarfs the bright galaxies themselves. But here's the thing: if this mysterious substance were actually visible, it wouldn't be called dark matter at all. The very definition of this material depends on its invisibility. Its weight remains hidden, and within that concealment lies one of the greatest puzzles in all of science. Scientists describe this dark matter as cold, which might sound strange when talking about something in the vacuum of space. Cold here doesn't mean temperature. It means this matter moves slowly compared to the speed of light. This sluggish movement turns out to be crucial for the universe as we know it. The slow speed allows dark matter to clump together and build structures over billions of years. If it moved too fast, like certain particles called neutrinos, it would spread out too evenly across space. Galaxies would never form because there wouldn't be enough gravitational pull in any one region to gather ordinary matter together. Instead, this cold, dark matter settles into invisible halos around regions of space. These halos create gravitational wells, like cosmic valleys where gas can fall inward and eventually form stars. For billions of years, this invisible weight has been quietly sculpting the architecture of everything we see in the night sky. When we step back and consider this reality, something profound emerges. The material we can see, touch, and measure directly isn't the main character in the cosmic story. It's more like decoration on an invisible foundation. The stars that inspire poets and guide travelers are beautiful additions to structures built from something we cannot perceive. Galaxies are essentially lights mounted on scaffolding, made of dark matter. What we consider normal, the visible universe, is actually the exception. The invisible components represent the rule. Astronomers mapping the cosmos understand this strange truth. The bright galaxies scattered across their images are really just markers, like streetlights illuminating an invisible road system. The true map of the universe gets drawn by gravity itself, tracing the weight of matter that doesn't shine. Stretching across billions of light years, the cosmic web consists primarily of dark matter filaments. Galaxies collect along these filaments like dewdrops gathering on strands of an enormous spiderweb. The galaxies are luminous and beautiful, but they depend entirely on threads we cannot see. This invisible foundation also shapes what happens next in the cosmic story. As space itself continues expanding, dark matter provides the structural framework within which galaxies grow and change over time. Its gravity works against the expansion, though not strongly enough to stop it completely. Meanwhile, an even more mysterious force called dark energy drives the acceleration of cosmic expansion. The ongoing balance between these competing influences will determine the ultimate fate of everything. Without dark matter providing resistance, there would be no cosmic competition at all. Dark energy would dominate from the beginning, and the universe would expand so rapidly that no structures could ever form. Stars wouldn't exist, galaxies wouldn't exist, we wouldn't exist to ask these questions. The very fact that we're here to wonder about these mysteries serves as evidence for dark matter's essential role. The universe teaches us something quietly profound through this hidden reality. What matters most in any system isn't always what catches our attention. The greatest influences often work in silence, unseen, but absolutely essential. Every star that captures your imagination, every galaxy photograph that fills you with wonder, exists only because invisible matter holds it in place. The entire cosmos balances on a foundation we cannot perceive directly. Think about times you've built something yourself, whether it's assembling furniture or working on a craft project. You quickly learn the importance of good connections between parts. A jigsaw puzzle holds together through patience and careful fitting of edges. But more complex structures, like houses or bridges, or even simple paper crafts, often need something extra that binds all the pieces into a unified whole. Stars and galaxies need that binding force too. Left to their own devices, they wouldn't maintain the intricate patterns we admire in telescope images. They would gradually drift apart, their components scattering into the emptiness of space. Yet, they don't fall apart. They hold together reliably, orbit after orbit. For millions and billions of years, something acts as cosmic glue, not a sticky substance, but a force, an invisible presence that keeps everything organized. That binding agent is gravity, but gravity strengthened and shaped by the unseen mass of dark matter. To understand just how crucial this cosmic adhesive really is, picture a playground merry-go-round spinning with children hanging on. The kids near the center can grip the bars easily because the inward pull toward the middle overcomes their tendency to fly outward. But children sitting near the edge have to work much harder to stay on. The faster the merry-go-round spins, the more difficult it becomes for anyone to maintain their grip. Now imagine scaling that simple playground scene up to something millions of light years across. Stars orbiting near the outer edges of galaxies move at speeds that should fling them outward into the darkness between galaxies. The visible matter in the galaxy center shouldn't provide enough gravitational pull to hold on to these distant, fast-moving stars. Yet generation after generation of stars continues following their orbital paths, bound by gravitational forces that exceed what visible matter alone could supply. The invisible weight of dark matter provides the extra adhesive strength needed to prevent galaxies from unraveling. This cosmic glue doesn't work only within individual galaxies. It binds together clusters of galaxies, which represent the largest gravitationally connected structures anywhere in the universe. These galaxy clusters contain hundreds, or sometimes thousands of individual galaxies. The galaxies within these clusters zip around at tremendous speeds, far too fast for the gravity of visible matter to explain why they stay grouped together. If we calculated the gravitational forces based only on what we can see directly, these clusters should be completely unstable. The member galaxies should have scattered into space long ago. But when dark matter gets included in the calculations, everything makes sense. Invisible halos of dark matter surround not just individual galaxies, but entire galaxy clusters. These halos act like enormous gravitational cushions, providing the binding strength needed to keep all that luminous matter gathered together in stable configurations. The concept of invisible glue holding the universe together strikes us as both familiar and astounding. Familiar because we encounter binding agents constantly in everyday life. Astounding because this cosmic adhesive consists entirely of something beyond our direct perception. It exists purely through gravitational influence. It doesn't shine, doesn't emit heat, doesn't interact with light in any detectable way, yet it's stronger and more influential than all the brilliant stars and galaxies combined. One of the most compelling pieces of evidence for this cosmic binding agent comes from studying the very early universe. Just after the Big Bang, Space was filled with an incredibly hot, dense mixture of particles and radiation. Matter and light were coupled together so tightly that they constantly scattered off each other, preventing any stable structures from forming. As the universe expanded and cooled down, light finally decoupled from matter, leaving behind what scientists call the cosmic microwave background radiation. This ancient light still reaches Earth today, though billions of years of cosmic expansion have stretched it from visible light into microwave radiation. Embedded within this background radiation are tiny temperature variations, subtle ripples that reflect how matter was distributed when the universe was only about 380,000 years old. These ripples tell an important story about cosmic glue. If only ordinary matter had been available in the early universe, it wouldn't have clumped together quickly enough to form galaxies and stars within the time that was actually available. The gravitational binding power of dark matter was necessary to create the initial seeds of cosmic structure. Dark matter provided invisible scaffolding, gravitational wells into which ordinary matter could fall and begin building the luminous structures we observe today. Without that extra gravitational adhesive, the bright, star-filled universe we inhabit simply wouldn't have emerged from the cosmic background. The cosmic web that surrounds us operates on principles that challenge our everyday understanding of permanence. When we think about what lasts, our minds turn to concrete things, solid objects we can touch and feel. A boulder seems eternal compared to a butterfly. A mountain appears to outlast generations of wildflowers that bloom and wither at its base. But the universe operates by different rules entirely. Out there in space, the things that shine are actually the most temporary. Stars burn through their fuel like cosmic candles, flickering for millions or billions of years before they collapse into themselves, or explode in spectacular death throes. Gas clouds that stretch across light years compress into new stars, then disperse again. Planets form from swirling debris, develop surfaces and atmospheres, then gradually crumble back into dust. Everything that glows, everything that catches our attention, is constantly changing. Yet something invisible provides the backbone for all of this activity. Dark matter forms halos around galaxies, vast spheres of unseen material that extend far beyond the visible edges of star clusters. These halos persist while stars are born and die within them. They maintain their shape and influence across billions of years, providing a kind of stability that visible matter simply cannot match. This creates a peculiar reversal of our normal expectations. The substance we can see, measure directly, and photograph with telescopes turns out to be the restless, temporary component of the universe. The permanent foundation, the thing that holds everything together across cosmic time, remains completely invisible to us. We pass through it every second of our lives, without the slightest sensation. Scientists have learned to visualize this hidden architecture through computer simulations. They program the known laws of physics into powerful computers, add the expansion rate of the universe, input the amounts of regular matter they can detect, then include dark matter in the calculations. When they run these digital universes forward from the smooth, nearly uniform conditions that existed shortly after the Big Bang, something remarkable emerges. Long filaments of invisible matter begin to form, stretching across millions of light years. These strands connect with each other, creating a three-dimensional web that spans the entire simulated universe. Regular matter, the stuff that makes stars and planets, gets drawn toward the densest parts of this web. Galaxies form like dewdrops collecting along spider silk. Where multiple filaments intersect, massive galaxy clusters develop, containing thousands of individual star systems. The resulting structure matches what astronomers observe when they map the real universe. But when researchers run the same simulations without including dark matter, everything falls apart. Galaxies never form properly. The large-scale structure never develops. The cosmic web fails to appear. The invisible component turns out to be absolutely essential for creating the universe we actually live in. This creates a strange relationship between us and the most important substance in existence. Dark matter surrounds the Earth constantly. It fills the solar system, It forms a vast halo around our entire galaxy. Its particles, assuming they are particles, pass through your body, through the walls of buildings, through the solid rock of the Earth itself, without interacting in any detectable way. You are swimming in an ocean of dark matter every moment of your life, but it might as well not exist from your perspective. This situation reveals something profound about the limits of direct experience. If human knowledge were restricted only to things we can touch, see, hear, smell, and taste, we would never discover dark matter at all. Our senses are completely blind to the substance that outweighs all the stars. Only through careful measurement, patient observation, and mathematical analysis have we learned to detect its presence indirectly. The discovery continues a long tradition of scientific insights that have gradually displaced humanity from the center of things. For centuries, people believed the Earth was the focal point of creation, with everything else revolving around our world. Then we learned that Earth orbits the Sun, making our planet just one of several in the solar system. Later discoveries revealed that the Sun itself is an ordinary star among hundreds of billions in the Milky Way galaxy. Eventually, astronomers realized that our galaxy is just one among countless others, scattered throughout an expanding universe. Each step in this progression has made human beings seem smaller and less central to the cosmic story. Dark matter adds another chapter to this humbling narrative. Not only are we not at the center of the universe, we are not even made of the main ingredient. The atoms that compose our bodies, the same atoms that make up the Earth and Sun, and all visible stars, represent only about 15% of all the matter in the universe. We are constructed from what amounts to cosmic debris, trace contaminants in a universe dominated by something else entirely. The majority substance, the material that actually controls how galaxies form and evolve, is completely alien to our direct experience. Yet this knowledge carries an odd form of comfort. The same dark matter that binds distant galaxy clusters also holds our own Milky Way together. It guided the formation of the star that became our Sun. It influenced the distribution of gas and dust that eventually condensed into the solar system. Without dark matter providing gravitational scaffolding, the chain of events that led to Earth, and ultimately to life itself, could never have unfolded. We exist because of this invisible glue, even though we cannot sense it. Our entire evolutionary history has played out within a dark matter halo, shaped by forces we cannot feel. The substance that seems most foreign to human experience is actually intimately connected to our existence. The true nature of dark matter remains one of the biggest mysteries in modern physics. Many scientists suspect it consists of exotic particles that interact only through gravity, remaining invisible because they neither emit nor absorb light. Underground detectors wait in deep mines and tunnels, hoping to catch rare collisions between dark matter particles and ordinary signs. Space telescopes scan the sky, looking for subtle gravitational effects that might reveal dark matter concentrations. Other researchers propose that dark matter might not be a substance at all, but rather evidence that our understanding of gravity itself needs revision. Perhaps Einstein's equations, so successful at describing gravity on the scale of the solar system, break down when applied to entire galaxies. Maybe the apparent effects of dark matter actually result from modifications to gravitational physics that only become apparent across vast distances. Underground laboratories continue their patient vigil. Particle accelerators push to higher and higher energies, hoping to create dark matter particles in controlled collisions. Astronomers map the cosmic web in ever greater detail, tracing the invisible scaffolding through its effects on visible matter. Regardless of which theory eventually proves correct, the observations all point to the same conclusion. Something beyond what we can see holds the universe together. The discovery of dark matter represents one of those moments in science when careful observation reveals that reality extends far beyond immediate appearances. An astronomer notices that galaxies rotate faster than they should, based on their visible mass. Another researcher measures the motions of galaxy clusters and finds they contain much more matter than anyone can account for. Slowly, through the accumulation of evidence, a new picture of the universe emerges. This process began in the early 20th century, with astronomers who had the patience to make precise measurements and the honesty to admit when those measurements did not match expectations. Fritz Zwicky, working in the 1930s, was among the first to recognize that something was missing from our cosmic inventory. Zwicky possessed a brilliant but abrasive personality, known for giving unflattering nicknames to colleagues who disagreed with his ideas. But his sharp tongue was matched by an equally sharp intellect, and he had the insight to realize that the universe contained far more matter than anyone could see. Back in the 1930s, a Swiss astronomer named Fritz Zwicky was peering into the cosmos, studying something called the Coma Cluster. This wasn't just a single galaxy, but a whole collection of galaxies, all bound together by the invisible hand of gravity. Think about it for a moment, these massive island universes, each containing billions of stars, all dancing together in space. Zwicky had a clever idea. If he could measure how fast these galaxies were moving within the cluster, he could figure out how much mass was needed to keep them all together. It's like watching cars on a racetrack. If they're going too fast for the barriers, they'll fly right off. The same principle applies to galaxies in a cluster. What Zwicky discovered left him stunned. The galaxies were moving way too fast. Based on all the stars he could see through his telescope, all that glowing visible matter, the cluster should have torn itself apart long ago. The galaxies should have scattered into the void like marbles rolling off a table. But there they were, still bound together, still dancing their cosmic dance. There was only one explanation that made sense. Something invisible, something massive, was holding everything together. Zwicky called this mysterious substance Dunkel Materie, which is just German for dark matter. The name stuck, and it captures something profound about our universe. Most of it might be completely invisible to us. At the time, Zwicky's colleagues weren't exactly thrilled with his discovery. The idea that most of the universe could be invisible seemed ridiculous. It challenged everything astronomers thought they knew about the cosmos. Zwicky himself didn't help his cause much. He had a reputation for being, well, difficult to work with. His blunt personality often rubbed people the wrong way. But the data was there, staring everyone in the face. Zwicky had stumbled upon something extraordinary, the first real hint that our universe is mostly hidden from view. It's humbling when you think about it. All of human history, all our observations of the night sky, and we'd been missing most of the story. For decades after Zwicky's discovery, the idea of dark matter just sat there, neither fully accepted nor completely forgotten. Astronomers kept studying galaxies and clusters, but they were focused on other questions. The missing mass problem was like an unsolved puzzle sitting on a shelf, waiting for someone to pick it up again. That someone turned out to be Vera Rubin, an American astronomer who started her career in the 1970s. This was a time when women in science faced enormous barriers. Getting opportunities was hard. Getting recognition was even harder. But Rubin was driven by pure curiosity, the kind that doesn't let obstacles stand in the way. Rubin had built a reputation for being incredibly careful and thorough in her work. This attention to detail would prove crucial when she decided to study how galaxies spin. Working with Kent Ford, she developed precise methods for measuring the rotation of galaxies, using powerful instruments called spectrographs. The expectation was straightforward. Galaxies should behave like our solar system. The Sun contains most of our solar system's mass, so planets farther out orbit more slowly than those closer in. Mercury races around the Sun, while distant Neptune takes its sweet time. Galaxies should work the same way, with stars near the center moving fast and stars at the edges moving slowly. But when Rubin looked at her data, something was clearly wrong. The stars at the edges of galaxies weren't slowing down at all. They were orbiting just as fast as stars near the galactic center. The rotation curves, as astronomers called them, stayed flat instead of declining with distance. There was only one way to explain this strange behavior. Galaxies had to contain far more mass than anyone could see. Something invisible was providing the extra gravity needed to keep those outer stars whipping around at high speed. It was like discovering that a carousel was spinning faster than it should, powered by some hidden motor. Rubin's work was revolutionary, not just because of what she found, but because her evidence was rock solid. She gathered data from galaxy after galaxy, and the pattern held up every time. This wasn't a fluke or a measurement error, it was a fundamental feature of how galaxies work. Unlike Zwicky's earlier claims, which people could dismiss as speculation, Rubin's results were impossible to ignore. She had proven that dark matter wasn't just hiding in galaxy clusters. It was everywhere, woven into the very fabric of every galaxy in the universe. Rubin herself was remarkably humble about her discovery. She once said she expected to find the rotation curves she was looking for, the ones that declined with distance. When she didn't find them, she thought she'd made a mistake somewhere. But as the data piled up, galaxy after galaxy showing the same flat rotation curves, the truth became undeniable. There's something beautiful about how science works sometimes. Rubin wasn't chasing grand theories or trying to revolutionize cosmology. She was just looking carefully, measuring precisely, and listening to what the universe was telling her. Her breakthrough came through patience and persistence, not flash or speculation. Other astronomers quickly joined the effort, confirming Rubin's results and extending them to more galaxies. Galaxy clusters also revealed the same pattern, far more mass than met the eye. By the end of the 20th century, dark matter had transformed from a fringe idea into one of the central mysteries of cosmology. The human story behind this discovery is just as fascinating as the science itself, and Rubin represented completely different approaches to astronomy. Zwicky was bold and outspoken, willing to make dramatic claims even when others doubted him. Rubin was quiet and methodical, building her case piece by careful piece. Both approaches were essential. Zwicky had the vision to see something extraordinary and the courage to announce it to the world. Rubin had the patience and skill to turn that vision into solid, undeniable evidence. Together, though, separated by decades, they changed how we understand our universe. It's also telling how long it took for the scientific community to accept dark matter. Science likes to think of itself as objective, that it's still done by humans with all their biases and preconceptions. The idea that most of the universe is invisible challenged common sense in a fundamental way. It forced astronomers to admit that their most trusted tool, their eyes and telescopes, was showing them only a tiny fraction of reality. That's a hard pill to swallow. It took decades of mounting evidence before the scientific community fully embraced the idea that we live in a mostly invisible universe. When Rubin talked about her work later in life, she always emphasized the joy of discovery. She described the night sky not as some distant, cold expanse, but as something alive and full of secrets waiting to be uncovered. Her perspective brought warmth to what could otherwise feel like abstract mathematics and cold equations. Today, Rubin is celebrated as one of the pioneers of modern astronomy. Her observations remain fundamental to every discussion of dark matter. Yet for much of her career, recognition came slowly. She was often the only woman at scientific conferences, sometimes ignored or underestimated by her male colleagues. Still, she persevered, driven by curiosity, rather than the promise of fame or recognition. The fact that her work now stands as one of the pillars of modern cosmology is a testament to both her scientific skill and her determination to keep asking questions, even when the answers seemed impossible to find. When we look back at these early dark matter detectives, it becomes clear that scientific discovery is rarely a single eureka moment. It's more like a chain of observations, questions, and careful confirmations. Zwicky saw something strange and had the courage to name it. Rubin measured it precisely and proved it was real. Their story reminds us that the universe is far stranger and more mysterious than we ever imagined. Most of everything that exists is completely invisible to us, detectable only through its gravitational effects on the small fraction of matter we can actually see. It's a humbling thought, and one that should make us wonder what other secrets are hiding in plain sight. Scientists spent decades building on those early discoveries, each one adding another layer to our understanding. The universe doesn't give up its secrets all at once. It reveals them piece by piece, measurement by measurement. This is how science really works, not through sudden revelations, but through the patient accumulation of evidence by countless individuals who refused to ignore what the data was telling them. When Zwicky first noticed something strange about galaxy clusters, when Rubin saw those flat rotation curves, they could have dismissed these findings as measurement errors. Instead, they trusted what they observed, even when it challenged everything they thought they knew. That kind of intellectual courage, that willingness to follow evidence wherever it leads, that's what transforms curious observations into fundamental truths about reality. We're still living in that story today. The mystery of dark matter remains unsolved, despite decades of searching. We know it's there, we can map its influence, but we still don't know what it actually is. It's a humbling reminder that the universe is under no obligation to make sense to us on first glance. Step outside tonight and look up at the stars. Those points of light scattered across the darkness, they're not telling you the whole story. What you're seeing is maybe 5% of what's actually out there. The rest, the vast majority of the cosmos, remains invisible to your eyes, detectable only through its gravitational fingerprints. Every star you see is embedded in a vast halo of something we cannot directly observe. These stars orbit not just the visible matter at the galaxy's center, but something much more massive, much more extensive, something that outweighs all the shining matter by a factor of 5 to 1. It's like discovering that every person you meet is accompanied by 5 invisible companions, influencing every step they take. The way we detect dark matter is beautifully indirect. We can't photograph it, can't capture its light in our telescopes, because it doesn't interact with photons the way ordinary matter does. Instead, we watch how it shapes the dance of visible matter. Stars, galaxies, entire clusters of galaxies, all moving in ways that only make sense if something massive and unseen is choreographing their motions. Think about Vera Rubin's rotation curves, those careful measurements that showed stars at the edges of galaxies moving just as fast as those near the center. In our solar system, the outer planets crawl along their orbits while the inner planets race around the sun. That's what we expected to see in galaxies too. But galaxies don't follow the same rules. Their outer regions spin at constant speeds, held in place by gravitational forces we can't directly see. It's as if you threw a ball expecting it to arc downward under gravity, but instead, it flew in a straight line. You'd immediately know some other force was acting on it, even if you couldn't see what that force was. The unexpected motion of the ball would be your clue to the invisible influence. This same principle works on much larger scales. Galaxy clusters, those vast collections of hundreds or thousands of galaxies, they're moving too fast for their own good. If only visible matter was holding them together, they should have flown apart long ago. The fact that they remain gravitationally bound tells us something massive is keeping them together, something we can't see directly. The hot gas between galaxies in these clusters glows with X-ray radiation, adding to the visible inventory. But even when you count every star and all that hot gas, it's nowhere near enough mass to explain the gravitational binding. The clusters are like cities held together by an invisible foundation, their stability pointing to forces we can map but not directly observe. Perhaps the most elegant evidence comes from gravitational lensing, Einstein's gift to astronomy. Massive objects warp the fabric of space-time itself, bending the path of light like a lens. When light from distant galaxies passes through galaxy clusters on its way to us, it gets distorted, stretched, sometimes multiplied into multiple images. These distortions allow astronomers to weigh the intervening clusters with remarkable precision. Time and again, the mass revealed by lensing far exceeds what can be accounted for by visible matter. It's like seeing a shadow on the wall that's much larger than the object, casting it, immediately telling you something else must be present. The Bullet cluster provides one of the most dramatic examples. This system caught 2 galaxy clusters in the aftermath of a cosmic collision. The hot gas from both clusters crashed together and piled up in the middle, visible as a bright X-ray glow. But the gravitational lensing revealed that most of the mass had sailed right through, continuing outward with the galaxies themselves. This separation of visible matter from gravitational mass offers compelling evidence that dark matter behaves differently from ordinary matter. While the gas particles collided and stuck together, the dark matter particles passed through each other like ghosts, interacting only gravitationally. It's a cosmic demonstration that two different types of matter coexist in our universe. These gravitational signatures appear everywhere we look. The cosmic microwave background, that faint afterglow from when the universe first became transparent, carries the imprint of dark matter in its temperature variations. The tiny, hot and cold spots mapped across the entire sky reflect density fluctuations from the early universe, patterns that only make sense when dark matter is included in our models. Even in that ancient light, 13 billion years old, we can read the influence of invisible matter. It's as if dark matter signed its name in the first light of creation, leaving a signature we can still detect today. Without dark matter's gravitational scaffolding, the universe as we know it simply could not have formed. This way of knowing through indirect evidence is deeply human. We constantly navigate the world by reading signs and shadows, rather than seeing things directly. You know someone is home, not because you see them, but because the lights are on. You know it's windy not because you see air molecules moving, but because you see leaves rustling. You know someone is thinking not because you can observe thoughts, but because you can hear their words or see their expressions. Dark matter operates on this same principle, just scaled up to cosmic proportions. It makes itself known through consequences, through the behavior of things we can observe. The motion of stars writes dark matter's presence into the night sky as clearly as footprints in snow. Write the presence of an animal you never saw passing by. This isn't even unprecedented in astronomy. Neptune was discovered through its gravitational influence before anyone laid eyes on it. Astronomers noticed that Uranus wasn't following the predicted orbital path. Something had to be tugging on it. Mathematical calculations pinpointed where this unknown object should be, and when telescopes looked in that direction, there was Neptune, right where the math said it would be. Dark matter extends this same detective work to the entire universe. Instead of one hidden planet revealed by its pull on another, we're dealing with an entire hidden component of reality, one that outweighs everything we can see. It's the difference between finding a missing person and discovering that most of the population was invisible all along. Dark matter outweighs everything visible in the universe by a factor of 5. Think about that for a moment. The shadow, cast by invisible mass, isn't just a small correction to our understanding. It's actually the main feature of cosmic reality. When astronomers discovered Neptune, they were looking for a single missing planet. The math didn't quite add up, so they knew something was out there. Dark matter presents a similar puzzle, but on an unimaginably larger scale. The missing mass isn't just one object, it's most of the universe itself. Some researchers wondered if gravity might work differently on cosmic scales. Maybe the laws we use for galaxies and galaxy clusters need updating. These modified gravity theories offer intriguing possibilities. But when you look at gravitational lensing, at the bullet cluster collision, at the cosmic microwave background radiation, dark matter explains the evidence much better than altered gravity alone. There's something beautifully ironic about our situation. For thousands of years, humans looked up at stars for guidance. The night sky provided navigation, inspiration, even a sense of certainty against the unknown. Stars were sources of light, pushing back the darkness. Now those same stars tell us about an even deeper darkness. Their light doesn't solve the mystery, it actually makes it more profound. The shadows cast by starlight reveal something fundamental about reality. Knowledge doesn't always come from what shines brightest. Sometimes it comes from what remains completely hidden. Modern space telescopes create three-dimensional maps of dark matter distribution by studying gravitational lensing effects. Ground-based observatories measure galaxy motions with incredible precision. Each new dataset adds detail to the shadows, turning vague impressions into sharp outlines. We can't see dark matter directly, but we can trace its contours across the entire universe. The more we map these invisible structures, the more we realize how deeply they shape everything around us. Galaxies don't exist in isolation, floating randomly through empty space. They form along filaments of dark matter, like pearls on invisible strings. Galaxy clusters sit at the intersections of these filaments, like knots in a vast cosmic web. Stars are strung along scaffolding we cannot see. Their positions are dictated by gravity we cannot detect. The pattern of starlight across the sky is actually cast by shadows, by the invisible architecture of the cosmos. This challenges our relationship with seeing itself. Vision gives us confidence in the world around us. We trust what we can observe directly. But dark matter teaches us that sight isn't the final authority on reality. What we see is just the beginning of understanding. True comprehension comes from combining the visible with the implied, the seen with the unseen. The shadows in starlight remind us that reality extends far beyond what our eyes can reach. This might feel unsettling at first, but it can also feel strangely comforting. The universe is larger, deeper, more mysterious than it appears on the surface. Stars aren't lonely points of light, scattered randomly across space. They're part of a hidden structure, bound together by forces we're only beginning to understand. Living in such a universe means accepting that mystery is part of reality itself, not something that interrupts or disturbs it. The stars shine, and in their shining, they reveal more than just themselves. They reveal the presence of something greater, something invisible but undeniable. The universe isn't just filled with dark matter, it's also expanding. Space itself stretches, carrying galaxies apart like dots on an inflating balloon. This isn't motion in the usual sense, like planets orbiting or comets tracing paths across the sky. The fabric of reality itself is growing larger. Edwin Hubble discovered this expansion in the 1920s by measuring light from distant galaxies. Almost all of them showed redshift, meaning their light was stretched to longer wavelengths as they moved away from us. The farther away a galaxy was, the faster it seemed to recede. This wasn't the result of some central explosion sending everything outward. Space itself was expanding, carrying every galaxy along for the ride. At first glance, dark matter might seem irrelevant to cosmic expansion. After all, expansion involves the geometry of space and the influence of dark energy, that mysterious force driving accelerated growth. But dark matter has been present from the very beginning, and its gravity played a crucial role in how expansion shaped the universe we see today. Without dark matter, the universe would have expanded into smooth emptiness. Matter would have been spread too evenly to form galaxies, stars, or anything interesting at all. In the earliest moments after the Big Bang, matter and radiation were coupled together in dense, hot plasma. Tiny fluctuations in density existed, minute differences of maybe 1 part in 100,000. These were like faint ripples on a cosmic pond. On their own, these ripples might not have grown into anything significant. Radiation pressure from light kept pushing against the clumping of ordinary matter, smoothing everything out. But dark matter was different. It didn't interact with light at all. It was free to clump under its own gravity, even while radiation held ordinary matter at bay. As the universe expanded and cooled, these clumps of dark matter grew larger. They became the seeds of cosmic structure, the gravitational wells into which gas and stars would eventually fall. When light finally decoupled from matter, about 380,000 years after the Big Bang, the scaffolding of dark matter was already in place. This moment left behind the cosmic microwave background, a faint glow we can still detect today. By then, ordinary matter could settle into the gravitational wells created by dark matter. Without this invisible passenger riding along through cosmic expansion, the luminous universe simply wouldn't exist. The patterns in the cosmic microwave background encode the distribution of matter from that ancient time. Satellites have mapped these patterns with extraordinary precision, revealing subtle variations in temperature across the sky. When scientists compare this data with theoretical models, the fingerprints of dark matter become clear. Computer models show something remarkable when scientists try to recreate the universe we see. The ordinary matter we can touch and observe, it simply isn't enough to build the cosmic structures around us. When researchers add dark matter to their simulations, suddenly everything clicks into place. The models start matching what we actually observe in the night sky. This invisible passenger has left traces in the most ancient light the universe still carries. We're talking about radiation that's been traveling for nearly 14 billion years. And even there, we can detect dark matter's subtle influence. The expansion of space itself creates a fascinating tension. Galaxies race away from each other, and the farther they are, the faster they retreat. But dark matter works against this cosmic stretching, pulling ordinary matter together into the clusters and web-like filaments we see today. Picture bread dough rising in an oven, with raisins scattered throughout. As the dough expands, those raisins naturally move apart from each other. Now imagine you've somehow mixed in tiny invisible weights, creating pockets of extra density. Those heavier regions would pull nearby raisins toward them, creating clumps even as the overall expansion continues. Dark matter behaves exactly like those hidden weights. It gathers material together, resists the universal expansion, and sculpts the architecture of space while everything else spreads outward. Astronomers call this ongoing process structure formation. It's essentially a cosmic tug-of-war between expansion pushing matter apart and gravity, boosted by dark matter, pulling it back together. This delicate balance determines the fundamental shape and organization of everything we see. In the universe's early chapters, gravity held the upper hand in local regions. Dark matter began forming the first invisible scaffolds, what scientists call halos. Over billions of years, ordinary matter fell into these gravitational wells, and galaxies began to shine within them. Clusters formed where these structures intersected, gradually weaving the cosmic web we observe today. Later, as the universe aged, dark energy started dominating the expansion, stretching that web even further apart. Through all of this cosmic evolution, dark matter remained the quiet architect, binding structures together even as space itself continued growing. The precision of this balance is almost unsettling when you really think about it. If dark matter had been absent, or present, in much smaller amounts, the universe's expansion would have smoothed everything into a nearly uniform, featureless expanse. No galaxies, no stars, no planets, just an endless, bland distribution of matter. On the other hand, if dark matter had been far more abundant, its gravitational pull might have overwhelmed the expansion entirely. The universe could have collapsed back in on itself long before stars had time to form, let alone evolve into the complex systems that eventually produced life. The actual proportions we observe, about 27% dark matter and only 5% ordinary matter, with the remainder being dark energy, seem perfectly calibrated. Just enough structure to create richness and complexity, just enough expansion to prevent total gravitational collapse. This balance appears written into the very foundation of reality itself. It makes you wonder about the deeper principles that govern not just what exists, but what can exist at all. Dark matter also fundamentally shapes how we understand the flow of cosmic time. The fact that we live in a universe organized enough to contain stars, planets, and eventually life, that's largely thanks to dark matter's gravitational persistence. Billions of years ago, when galaxies were still assembling themselves, dark matter provided the invisible framework. Today, as cosmic expansion continues accelerating, dark matter still binds galaxies internally, preventing them from simply flying apart into the void. In the far future, when dark energy becomes even more dominant, dark matter will likely continue holding individual galaxies together, even as the spaces between galaxy clusters grow unimaginably vast. The passenger, it seems, never abandons the journey. Large-scale astronomical surveys put these theories to the test by mapping millions of galaxies across different epochs of cosmic history. These massive projects reveal the intricate patterns of filaments and empty voids that make up the cosmic web. When astronomers compare these observations with computer simulations, the match is remarkable, but only when dark matter is included in the calculations. Expansion alone simply cannot produce the patterns we observe. Something invisible must be guiding the growth of structure across billions of years of cosmic evolution. This understanding completely transforms how we interpret the night sky. Those stars above us aren't just randomly scattered points of light. They're arranged by an ancient collaboration between expansion and gravity, between dark energy pushing outward and dark matter pulling inward. Every galaxy, every cluster, represents the outcome of this hidden partnership. The balance between these opposing forces has literally written the universe we inhabit. Imagine for a moment that you could actually see dark matter, not as glowing particles, but as a faint outline revealing the true architecture of space. You would see vast filaments stretching across distances that dwarf entire galaxies, like cosmic threads with galaxies strung along them like luminous beads. Around every galaxy, you would see invisible halos, ghostly bubbles of mass, cradling those familiar spiral disks. Galaxy clusters would appear, wrapped in cocoons of unseen gravity, slowly colliding and passing through each other in gravitational dances that span hundreds of millions of years. The expansion would still carry everything outward, but you would finally see how the passenger shapes the entire ride. The mysterious nature of this cosmic passenger raises profound questions that keep physicists awake at night. What is it actually made of? How does it behave on the smallest possible scales? Does it interact with anything besides gravity? Teams around the world continue designing increasingly sensitive detectors, building more powerful particle accelerators, launching sophisticated satellites, all hoping to catch the faintest direct sign of dark matter. The answer remains frustratingly elusive, but the evidence for its existence is absolutely overwhelming. Something unseen has been traveling with the universe since its earliest moments, and without this invisible companion, the cosmos would be completely unrecognizable. There's something almost poetic about how the most fundamental truths often remain hidden from direct observation. You can live your entire life without noticing the expansion of the universe, because locally, gravity and dark matter keep Earth bound to the sun bound to our galaxy. You can gaze at stars and never realize that most of their story is written in invisible scaffolding surrounding them. The expansion operates on scales too vast to perceive directly. The passengers remain silent, and yet together they define absolutely everything we see. When most people picture galaxies, they think of spirals. Those magnificent pinwheel shapes captured in telescope images represent some of astronomy's most breathtaking sights. Arms of starlight curve gracefully outward from brilliant centers, winding like cosmic whirlpools frozen in space and time. Some spirals appear perfectly symmetrical, others more irregular and ragged, but they all share that sense of motion, that swirling balance between gravitational attraction and rotational momentum. It's not coincidental that these vast whirlpools provided one of the clearest early clues to the universe's hidden mass. In the precise way they spin, they carry the unmistakable signature of something invisible, holding them together against forces that should tear them apart. A galaxy, despite how it appears in photographs, isn't just a flat pattern painted across the sky. It's a fully three-dimensional system containing billions of individual stars, along with vast clouds of gas, dust, and dark matter, all orbiting around a common gravitational center. Each star follows its own elliptical path, guided by the collective gravity of the entire system. The result, when viewed from the immense distances between galaxies, creates those spiral patterns, arms composed of stars that appear to stream outward, like ripples spreading across a cosmic pond. But hidden beneath that graceful appearance lies a puzzle that confused astronomers for decades. These galactic whirlpools spin far too fast for their own good. If only the visible matter existed, the stars along the outer edges would be in constant danger of flying off into intergalactic space. Think of children riding a playground merry-go-round. Those near the center can hold on relatively easily, but the ones at the outer edge feel the strongest centrifugal force, trying to fling them away. In a galaxy, gravity provides the inward pull that should keep stars in their orbits. But that gravity comes from mass, and there simply isn't enough visible mass to account for the rotation speeds, astronomers observe. Stars deep in space follow paths that seem to break the rules we know. When you look at how fast they move around their galaxy's center, something strange emerges. The stars closer to the middle should race along quickly, pulled by all that mass. The ones farther out should crawl along slowly, just like how Neptune takes forever to circle our Sun compared to speedy Mercury. But galaxies don't follow this pattern at all. A scientist named Vera Rubin discovered something puzzling back in the 70s. She measured star speeds very carefully and found that stars way out on the edges move just as fast as the ones near the center. It's like finding that all the horses on a merry-go-round, whether they're on the inner ring or the outer edge, are somehow keeping the same pace. This discovery transformed how we see these cosmic whirlpools. The beautiful spiral arms that photographs capture, they shouldn't be able to hold together without some extra invisible mass providing gravity. Those graceful curves would unwind like a loose spring. The stars would drift away into the emptiness between galaxies. Think about what this means for a moment. Every galaxy we admire, with its sweeping arms and glowing center, sits inside something we cannot see. This invisible halo wraps around the visible parts like a giant transparent bubble. The glowing disk of stars, all that beauty we photograph, makes up only a tiny fraction of what's actually there. Galaxies have been spinning for over 10 billion years. That's a staggering amount of time, enough for the outer regions to fly apart many times over if they only had visible matter holding them together. Yet here they are, still intact, still recognizable. Something invisible acts like cosmic glue, keeping everything bound together through countless generations of stars. This hidden mass reveals its nature through what it doesn't do. If it were made of ordinary stuff, dim stars or cold gas clouds, it would interact with light somehow. It might absorb certain wavelengths, or scatter them, or glow faintly. But these halos show none of these signatures. They announce themselves purely through gravity, pulling on things, but remaining completely dark. Scientists run computer simulations to understand how galaxies form. When they input only the matter we can see, the results look nothing like real galaxies. The structures collapse in on themselves or spread out too thin. The spiral arms fail to develop. But when they add invisible dark matter halos to their calculations, perfect spiral galaxies emerge on the screen. There's something beautifully ironic about this situation. The very features that make galaxies so photogenic, those elegant spiral arms, are actually signposts pointing to something invisible. The whirlpool pattern exists because of mass we cannot detect. The luminous parts depend entirely on their dark companions. This phenomenon isn't limited to spiral galaxies either. Elliptical galaxies, those smooth balls of stars without much structure, also show the same strange behavior. Their stars move in ways that only make sense if invisible mass surrounds them. Even irregular galaxies, ragged and chaotic looking, float inside halos that outweigh them many times over. And the universality of this pattern strengthens the evidence significantly. Every single galaxy, regardless of its shape or size, shows signs of being embedded in dark matter. It's not some quirky behavior that only affects certain types. It appears to be a fundamental feature of how the universe works. These invisible halos extend far beyond where the stars shine. If you picture our Milky Way as a disk about 100,000 light-years across, its dark matter halo probably stretches out 3 times farther in every direction. We live deep inside this invisible sphere, completely unaware of its presence, as we go about our daily lives. This reframes our cosmic address in a profound way. We're not just residents of a spiral galaxy, we're passengers floating inside a much larger invisible structure that holds everything together. The sun's orbit around the galactic center, the formation of new stars, even the movement of gas between stars, all of these processes are governed by dark matter's gravitational influence. When you look up at the night sky, you're unknowingly experiencing dark matter's effects. Every star position, every constellation pattern, reflects the invisible scaffolding that keeps our galaxy stable. The ordinary matter we see is just foam on top of a much deeper ocean. Galaxy collisions reveal even more about these hidden structures. When 2 galaxies approach each other, their visible parts can get stretched and distorted dramatically. Stars get flung out in long tidal tails, spiral arms get warped beyond recognition. But the dark matter halos cushion these impacts, binding the systems together even as their luminous parts get scrambled. Our own galaxy faces such an encounter in the future. The Andromeda Galaxy, another spiral whirlpool, with its own massive dark halo, approaches us slowly through space. In about 4 billion years, these two systems will collide and merge. The stars themselves will mostly pass by each other harmlessly, but the dark matter halos will blend together, creating an even larger, invisible sphere. Individual galaxies also cluster together in groups and larger structures. These galaxy clusters contain hundreds or thousands of members, all held together by gravity. But when astronomers add up all the visible matter in these clusters, they find the same problem on an even grander scale. There isn't nearly enough ordinary matter to explain why these galaxy collections hold together. The hot gas between galaxies in these clusters glows in X-rays, revealing temperatures of millions of degrees. This gas should be expanding and escaping into space, but something holds it in place. Dark matter provides the extra gravitational pull needed to contain this superheated material. Some of the most compelling evidence comes from galaxy cluster collisions. When two massive clusters slam into each other, the dark matter and ordinary matter behave differently. The ordinary matter, including those X-ray glowing gas clouds, gets slowed down by friction and pressure, but dark matter passes right through, since it only interacts through gravity. Telescopes can map where different types of matter end up after these cosmic crashes. The ordinary matter lags behind, while the dark matter races ahead to where gravity says most of the mass should be. It's like watching an invisible parade where you can only see some of the participants. These observations paint a picture of a universe where the stuff we're familiar with plays a supporting role. Dark matter outweighs ordinary matter by about 5 to 1 throughout the cosmos. The atoms that make up stars, planets, and people represent just a small minority of all the matter that exists. This has philosophical implications that extend beyond astronomy. We evolved to perceive and interact with ordinary matter, the kind made of atoms. Our senses, our tools, our entire understanding of physics developed around this familiar substance. Yet the universe is dominated by something completely different, something that reveals itself only through its gravitational effects. The whirlpool galaxies that inspired generations of astronomers are really just the visible tips of much larger, invisible icebergs. Their beauty emerges from hidden foundations we're only beginning to understand. The cosmos operates according to rules that remain largely mysterious, governed by substances that exist beyond our direct experience. Dark matter doesn't just sit quietly in the background of our universe. It actively shapes everything we see, influencing how galaxies form, grow, and eventually merge with one another. The beautiful spiral arms we observe in galaxies are really just the visible surface of something much deeper, something we can't directly see. Think of it like foam floating on ocean waves. The foam is lovely to look at, but the real power lies in the unseen water beneath. When astronomers study these galactic whirlpools in greater detail, they discover that dark matter halos come in different varieties. Some galaxies seem to have dark matter cores with fairly uniform density throughout, while others show much steeper profiles where the dark matter clumps more tightly. These subtle differences might actually tell us something fundamental about what dark matter particles are really like, whether they're cold and sticky, clumping together easily, or warm and smooth, spreading out more evenly through space. Every time we look at a galaxy, we're witnessing one of science's greatest puzzles. Those spiral patterns aren't just pretty arrangements of starlight, they're actually signatures, fingerprints left behind by invisible matter. These cosmic structures spin on foundations we cannot see, like sculptures carved by a gravity that refuses to reveal its true source. For centuries, light seemed like the most reliable messenger in the universe. It travels at nature's ultimate speed limit, carrying images from the most distant corners of space and time. A telescope is essentially a sophisticated net designed to catch this ancient light and show us stars, galaxies, and nebulae exactly as they appeared when that light first began its journey toward us. Astronomers used to think light traveled in perfectly straight lines, following invisible highways from source to observer. But Einstein's theory of general relativity completely revolutionized this understanding. According to relativity, space itself can actually bend and curve, and light, which always follows the straightest path available, must follow those curves. When space warps, light warps with it. This idea seemed almost impossibly strange when Einstein first proposed it. The notion that empty space could be twisted and shaped by mass wasn't something people found easy to imagine. But in 1919, during a solar eclipse, astronomers made a remarkable observation. Stars that appeared near the sun in the sky looked slightly shifted from their expected positions. The sun's gravity had actually bent their light during its journey to Earth. The effect was tiny, but it was real, and it confirmed Einstein's predictions while introducing us to gravitational lensing. Gravitational lensing turned out to be far more than just an interesting curiosity. It became one of our most powerful tools for understanding the universe, allowing us to measure mass in ways that don't depend on light at all. Wherever light bends, mass must be present, and when astronomers apply this technique systematically, they consistently find much more mass than what we can actually see. This invisible scaffolding reveals itself through different types of lensing effects. Sometimes the bending is dramatic and obvious. A distant quasar might appear doubled, tripled, or even quadrupled, its light split into multiple images by a galaxy sitting between the quasar and Earth. These strong lenses can create arcs, rings, and other spectacular patterns across the sky. Other times the bending is much more subtle, producing only slight distortions in the shapes of background galaxies. This weak lensing might not look impressive in individual cases, but when measured statistically across thousands or millions of galaxies, it reveals maps of mass distribution spanning enormous cosmic distances. One of the most beautiful examples of strong lensing is called an Einstein ring. When a distant galaxy or quasar lies almost perfectly behind a massive foreground object, its light gets bent into a complete circle around the lensing mass. These rings make the geometry of curved spacetime visible to our eyes, creating luminous outlines of invisible gravity at work. They're not just stunning to look at, they're also precision instruments for measuring mass, including both the visible and invisible components of lensing galaxies. Weak lensing has become absolutely fundamental to modern cosmology. By studying the tiny elongations of millions of background galaxies, astronomers can map the dark matter lying between us and those distant objects. The resulting maps show a universe woven together with filaments and knots of unseen mass, matching remarkably well with computer simulations of cosmic evolution. These large surveys reveal that galaxies and clusters aren't isolated islands floating in empty space. Instead, they're embedded in a vast cosmic web of dark matter that stretches across billions of light years. The web casts shadows, distorting starlight in ways that outline the invisible architecture of our universe. Perhaps the most compelling single piece of evidence for dark matter through lensing comes from something called the bullet cluster. This system formed when two galaxy clusters collided, creating a natural laboratory for studying different types of matter. During the collision, the hot gas clouds from each cluster interacted, slowed down, and merged in the center of the collision zone. The individual galaxies, being relatively tiny compared to the vast spaces between them, mostly passed through without colliding. But when astronomers used lensing to measure where the mass actually was, they discovered something remarkable. Most of the mass wasn't located in the center, with the merged gas, but was instead aligned with the galaxies that had passed through the collision. This showed clearly that the majority of each cluster's mass exists as dark matter, which doesn't interact like ordinary matter, but simply continues on its path, influenced only by gravity. The bullet cluster is often described as smoking gun evidence for dark matter, because it so cleanly separates visible matter from invisible mass. You can literally see them in different places after the collision. Lensing studies have extended to even larger cosmic structures, examining superclusters and the vast empty regions called voids. The patterns of distortion across the sky match the presence of massive dark matter filaments connecting clusters. while leaving empty gaps in between. These cosmic maps, drawn not with ink but with bent starlight, confirm that the universe's true architecture is defined by dark matter. The galaxies we can see are merely decorations hanging on this hidden framework. There's something profoundly humbling about this realization. Light, the very thing we depend on to observe and understand the universe, can be deceived by gravity. A galaxy we think sits in one location might actually be somewhere else entirely, its light bent into an arc along the way to us. A background object might appear duplicated or stretched, its true form disguised by intervening mass. In this sense, the cosmos resembles a vast hall of mirrors, where light reveals not only what shines, but also what bends it. To read the universe correctly, we must learn to see through these cosmic lenses, to understand how gravity sculpts the light that carries information across space and time. The true power of gravitational lensing lies in its independence from assumptions about what kind of matter we're dealing with. It doesn't matter whether the unseen mass consists of exotic particles or something else entirely. Gravity bends light regardless of the source. The universe operates like a vast magnifying glass, though not in the way we might expect. Light traveling from distant stars gets twisted and stretched as it passes through regions where invisible mass lurks. This bending happens everywhere, constantly, whether we notice it or not. The sun does it. Galaxies do it. Even entire clusters of galaxies reshape the light that passes near them. What makes this fascinating is that light doesn't care what kind of matter it encounters. Ordinary stars, mysterious dark particles, even black holes, they all bend light in exactly the same way, according to their mass. The light simply follows the curves that gravity carves into space itself. This gives us something remarkable, a way to weigh things we cannot see. When astronomers point their telescopes at distant galaxies, they sometimes find images that look stretched, like reflections in a funhouse mirror. Other times, they see the same galaxy appearing multiple times in different spots, as if space itself were playing tricks with mirrors. These distortions aren't accidents or flaws in the instruments. They're signatures of invisible mass sitting between us and those distant lights. The really striking thing is how much bending occurs in places where very little visible matter exists. It's like watching shadows dance on a wall when you can't see what's casting them. The shadows are clear evidence that something substantial is there, even if your eyes can't make it out directly. In space, the bending light serves as those shadows, revealing the presence of dark matter halos wrapped around galaxies. This technique works across enormous distances and vast stretches of time. Because light takes billions of years to reach us from the most distant galaxies, we're essentially looking backward through cosmic history. By measuring how much bending occurred at different epochs, scientists can piece together how structures grew and evolved over time. The story that emerges is consistent. Dark matter was essential for building the large-scale architecture we observe today. The measurements involved are incredibly precise. Astronomers must detect shape changes of less than 1% across millions of galaxies. It's like trying to notice that a coin has been stretched into a slightly more oval shape, then doing this for millions of coins simultaneously while accounting for atmospheric blur and instrumental noise. Yet the effort pays off with something no other method can provide: a direct map of invisible mass distribution. There's something profound about how much of scientific discovery comes down to noticing when things aren't quite as they should be. A line that's not perfectly straight, a curve that doesn't follow the expected path, an image that appears in the wrong place or with the wrong shape. These tiny deviations from expectation often point toward the most important discoveries. In this case, the universe itself provides distorted images, and hidden within those distortions lies evidence for the dominant component of cosmic matter. Without this bending effect, the invisible would remain truly concealed. But because massive objects curve space-time, and light dutifully follows those curves, the hidden reveals itself through the very photons that travel across billions of light-years to reach our telescopes. Every massive object essentially becomes a lens, whether we realize it or not. The effect is always there, sometimes dramatic enough to create multiple images of the same distant galaxy, sometimes so subtle it requires statistical analysis across vast numbers of objects to detect, but it's always happening, a fundamental consequence of how gravity works in Einstein's universe. Future space missions and ground-based observatories promise to refine these cosmic maps even further. They'll peer deeper into space and time, measuring the dark matter distribution with unprecedented precision. Each new survey adds detail to our understanding of how the invisible scaffolding of the universe is arranged. When early astronomers first began mapping the heavens, they saw stars as isolated points scattered across the sky. Even after galaxies were recognized as vast collections of stars, they seemed like islands floating alone in empty space. But as surveys expanded and technology improved, a very different picture emerged. Galaxies weren't randomly distributed at all. Instead, they're arranged in an intricate pattern, stretched into long filaments, clustered into dense knots, separated by vast empty regions. On the largest scales, the universe resembles a three-dimensional web, with structure extending across hundreds of millions of light years, and the strands of this cosmic web are made primarily of dark matter. Think of a spider web covered in morning dew. The web itself is nearly invisible until water droplets cling to the strands, making the underlying structure visible by catching and reflecting light. In the universe, dark matter forms those invisible strands, and galaxies are like the dewdrops, glowing along the filaments and revealing the hidden architecture beneath. This discovery came gradually through massive surveys that mapped millions of galaxies in 3 dimensions. The results were stunning, revealing walls of galaxies forming superclusters, long filaments stretching across cosmic distances, and enormous voids where almost nothing exists. These patterns aren't random accidents. They're the direct result of dark matter's gravitational influence over billions of years. Computer simulations help us understand how this structure formed. Starting with tiny fluctuations in the early universe, dark matter began clumping under its own gravity. Ordinary matter, attracted to these growing dark matter concentrations, followed along. Over cosmic time, small clumps merged into larger ones, eventually forming the web-like pattern we observe today. Without dark matter's gravitational scaffolding, ordinary matter alone would never have arranged itself into such organized structures. It would have remained too smooth, too evenly distributed. The universe would lack the dramatic architecture of filaments and voids, the clustering of galaxies into superclusters, the intricate web that spans the observable cosmos. Each strand of this web represents a highway of sorts, along which matter and energy flow. Galaxies form where these cosmic highways intersect, fed by streams of gas flowing along the dark matter filaments. The largest galaxy clusters sit at major intersections, like cosmic cities connected by an invisible interstate system. The voids between filaments aren't truly empty, but they're remarkably sparse compared to the dense regions where galaxies congregate. These cosmic deserts stretch for hundreds of millions of light years, containing very few galaxies and representing the spaces between the web strands. Understanding this large-scale structure helps explain why galaxies have the properties they do. A galaxy's environment, whether it sits in a dense cluster or along a quiet filament, influences how it forms and evolves. The cosmic web doesn't just organize matter on the largest scales, it shapes the destiny of individual galaxies across cosmic time. When scientists run computer simulations of how the universe should have formed, something fascinating emerges. The virtual cosmos they create matches almost perfectly with what telescopes actually see out there. Those long threads of galaxies, those dense clusters, those vast empty regions, they all appear naturally in the simulation when dark matter gets included in the equations. But here's what makes you pause and think. When researchers remove dark matter from their digital universe, everything falls apart. The simulated cosmos looks completely different. Nothing like the real thing we observe through our instruments. This match between computer models and reality stands as one of the most compelling pieces of evidence that dark matter actually exists out there. The cosmic web stretches across distances that challenge human comprehension. A single thread of this invisible structure can extend for hundreds of millions of light years. Picture that for a moment, distances so vast that light itself traveling at the ultimate speed limit of the universe, takes hundreds of millions of years just to cross from one end to the other. Galaxy clusters sit at the intersections where these cosmic threads meet, like knots tied in an enormous net. Each cluster contains thousands of individual galaxies, and each galaxy holds billions of stars. Between these cosmic intersections lie voids, regions so incredibly empty that you could count entire galaxies on your fingers within spaces spanning tens of millions of light years. The scale staggers the imagination, yet the pattern remains remarkably clear. The universe, despite its apparent chaos, reveals itself as fundamentally structured. This structure, this cosmic architecture, gets written in the language of dark matter. One of the most remarkable aspects of this web involves its consistency. Astronomers can point their telescopes in any direction, toward any region of space, and the same pattern repeats itself. Whether they map nearby cosmic neighborhoods or peer billions of light years away into the distant past, the filaments and voids appear with reliable regularity. This consistency tells us something profound about the nature of reality, the laws of physics, the role of dark matter, the expansion of space itself. They all work together in ways that remain predictable across both time and distance. The web serves as a universal feature, present throughout the cosmos. For scientists who study individual galaxies, the web provides crucial context. A galaxy doesn't exist as some isolated island, evolving entirely on its own. Its cosmic environment shapes its destiny in fundamental ways. A galaxy living within a dense filament will grow and change differently from one drifting in a sparse region. Gas flows along these invisible highways, streaming toward galaxies and providing the raw material for new stars to ignite. Galaxies and clusters encounter each other more frequently along the filaments, sometimes colliding and merging into even larger systems. The web guides not only where galaxies form initially, but how they evolve over billions of years. Dark matter, though completely invisible to our eyes, shapes even the smallest details of galactic existence. The filaments function like cosmic highways, channeling matter and energy across vast distances. Gravity funnels gas streams along these invisible roads, feeding the knots where massive clusters eventually form. Over the course of billions of years, these flows have nourished the largest structures the universe contains. Without dark matter providing the gravitational framework, these flows simply wouldn't exist. Ordinary matter would drift apart, with the expansion of space too, diffuse to create such concentrated, organized features. The web reveals itself not as some static pattern frozen in time, but as a dynamic system actively channeling material and energy across cosmic scales. Even the largest voids, those seemingly empty spaces between filaments, tell their own story about dark matter's influence. These regions aren't completely devoid of matter, but they contain far less than average. They exist precisely because matter has been gravitationally pulled away into the filaments and clusters, leaving behind these underpopulated zones. When astronomers study the few galaxies that do exist within voids, they see how cosmic isolation affects galactic growth and evolution. The very existence of these empty regions provides yet another signature of dark matter's invisible hand, shaping the cosmos. Scientists have developed techniques to map the web directly, independent of the visible galaxies that trace its outline. Gravitational lensing allows them to detect the presence of mass by measuring how it bends and distorts light from more distant sources. By carefully analyzing how light from background galaxies gets warped as it travels through space, astronomers can trace the distribution of matter in the foreground. These lensing maps reveal filaments of dark matter. Even in regions where few galaxies shine, the web becomes visible not through its own illumination, but through its gravitational fingerprints on passing light. There's something almost paradoxical about this cosmic web that makes you reflect on the nature of reality itself. It represents the largest structure in the entire universe, yet remains completely invisible to direct observation. Its scale dwarfs every galaxy, every star, every planet, yet it cannot be seen with any telescope or instrument. We know it exists only because of the patterns it creates in the things we can observe. The galaxies themselves are merely traces, like morning dew clinging to invisible spider strands. The true web remains dark, extending far beyond our ability to imagine such scales. For many researchers, studying the cosmic web feels like reading the universe's fundamental blueprint. It reveals how matter first assembled in the early cosmos, how structure gradually grew over billions of years, and how dark matter guided the entire process from beginning to end. The web serves as both a map of cosmic history and a guide to the future. As the expansion of space continues, this web will stretch and evolve. Filaments will grow thinner. Clusters will become more isolated from one another. Dark matter will continue holding galaxies together within their local neighborhoods. But the larger connections may eventually fade from view as dark energy drives structures apart. The web we observe today captures just a single moment in a dynamic story that's been unfolding for billions of years. When you contemplate your place in this vast structure, it can feel overwhelming to realize that you're actually part of it all. Yet, that's precisely the truth of our situation. The Milky Way itself travels along one of these cosmic filaments, connected to clusters and voids that extend far beyond our local region of space. Our galaxy doesn't drift alone through empty darkness, but participates in this cosmic architecture, woven into the web like a single thread in a tapestry of unimaginable size. We may not see the strands directly with our eyes, but our very existence depends entirely upon them. Without this web, galaxies wouldn't occupy the positions they do, and life would never have emerged here to wonder about any of it. The ongoing study of cosmic web structure continues refining our understanding of dark matter's true nature. Different theoretical models predict slightly different types of structures should form. Cold dark matter, moving relatively slowly through space, creates filaments and clusters matching what we actually observe. Warm or hot dark matter, moving much faster, would have smoothed out the web during its formation, erasing the small-scale structures we see today. The fact that we observe such an intricate, detailed web strongly supports the cold dark matter model. The shape of the universe itself provides clues about the nature of this invisible component. The cosmic web stands as one of the most powerful pieces of evidence for dark matter's reality. It's too vast, too detailed, too consistent across time and space to be explained by any other known phenomenon. Galaxies trace its strands like lights outlining an invisible framework. Voids mark regions where it's absent, and gravitational lensing reveals its mass distribution. It forms the hidden skeleton upon which everything visible in the universe gets arranged. But this raises perhaps the deepest question of all. What exactly is this invisible substance that shapes everything we see? If it's not made of stars or glowing gas, then what particles or entities actually form this cosmic web? When you look up at the night sky, the most natural assumption suggests that everything out there must be made of the same basic stuff as stars. Those bright points of light are distant suns, those hazy patches are collections of suns, and the glowing band of the Milky Way represent billions of suns blended together into a river of light. For a very long time, it seemed reasonable to think that whatever the universe contained would all be constructed from this same luminous material. Stars appeared fundamental, the basic building blocks from which cosmic architecture gets assembled. But the more carefully astronomers measured and weighed the cosmos, the clearer it became that this assumption was completely wrong. The universe is not made mostly of stars or anything that shines. The galaxies we see, spectacular as they are, don't represent the whole story. The majority of matter out there is something else entirely, something that remains invisible, something that produces no light of its own. Looking up at the night sky, we see a universe painted in light. Stars twinkle, planets wander, galaxies spiral in distant splendor. For hundreds of years, this luminous display defined our entire understanding of what exists out there. Astronomers could only study what glowed, what reflected, what somehow interacted with light itself. This makes sense when you think about it. Our eyes evolved to see light. Our instruments were built to capture it. Everything we discovered from distant nebulae to speeding comets, revealed itself through photons reaching our detectors. Even those mysterious dark patches threading through the Milky Way, those cosmic shadows that puzzled early observers, turned out to be ordinary dust and gas. They were blocking light, not creating some fundamental mystery. The assumption seemed rock solid. Matter was matter, whether it glowed like a star or sat cold and dark like a planet. Everything followed the same rules, built from the same atomic ingredients we find here on Earth. Protons, neutrons, electrons, combining in endless varieties, but always following familiar patterns. This comfortable picture started developing cracks sometime in the middle of the last century. Astronomers began noticing something deeply strange. Galaxies were spinning too fast. Galaxy clusters were moving in ways that didn't make sense. The math kept pointing to the same uncomfortable conclusion. There wasn't enough visible matter to explain what they were seeing. At first, the solution seemed obvious. Maybe vast quantities of ordinary matter were simply hiding. Faint stars too dim to see directly, clouds of cold gas floating in the darkness, swarms of planets drifting through space. The universe could be filled with familiar materials that just happened to be hard to detect. But here's where things get interesting. Ordinary matter, even when it's not glowing, leaves traces. It interacts with light in predictable ways. Gas clouds absorb specific wavelengths, creating fingerprints in starlight. Dust particles scatter and block radiation. Even the faintest brown dwarf stars emit heat that sensitive instruments can detect. These signatures should be everywhere. If the missing mass were made of normal atoms, the numbers should add up. Instead, surveys kept coming up empty. The invisible halos surrounding galaxies were far too massive to be explained by hidden collections of ordinary material. This led to a rather unsettling realization. The missing matter wasn't just faint or well hidden. It was fundamentally different from everything we thought we knew about the universe. It didn't shine, didn't absorb, didn't scatter light at all. It seemed to ignore the electromagnetic force entirely, interacting only through gravity. Scientists gave this mysterious substance a deliberately simple name, dark matter, but the simplicity of the label masks something profound. If dark matter isn't made of atoms, then most of our universe consists of something completely outside the periodic table. Something beyond the chemistry that builds stars, planets, and life itself. Think about that for a moment. Every element we know, every chemical reaction, every material process represents only a small fraction of what actually exists. It's a humbling thought, reminiscent of ancient philosophers who wondered whether our senses could truly reveal reality's deeper nature. The evidence for this strange conclusion comes from multiple directions. The cosmic microwave background, that faint afterglow still echoing from the universe's birth, carries detailed information about matter's early distribution. Precise measurements reveal that ordinary atomic matter makes up only about 5% of everything that exists. Dark matter accounts for roughly 27%, with the remainder being the even more mysterious dark energy. These aren't rough estimates. The ratios emerge clearly from the patterns imprinted in that ancient radiation. The mathematics of the early universe, when matter first began clumping into the structures we see today, requires this specific balance between ordinary and dark components. Another compelling line of evidence comes from nucleosynthesis, the remarkable process that forged light elements during the universe's first few minutes. When temperatures were billions of degrees and nuclear reactions proceeded at furious rates, the density of ordinary matter determined exactly how much hydrogen, helium, and lithium would form. Observations of these primordial abundances match theoretical predictions with stunning precision, but only if ordinary matter represents that same small 5% fraction. If the missing mass consisted of ordinary atoms, these ratios would be completely wrong. The fact that they're exactly right confirms that most matter must be something else entirely. This realization sent astronomers on an intensive search for hidden ordinary matter. They coined the term MASHOs, massive compact halo objects, for all the possibilities that might be lurking invisibly in space. brown dwarf stars that never quite ignited, white dwarf remnants of long-dead stars, neutron stars compressed to incredible densities, even black holes scattered throughout galactic halos. The search employed clever techniques like gravitational microlensing. When a massive object passes in front of a background star, its gravity briefly magnifies the star's light, creating a telltale brightening event. By monitoring millions of stars simultaneously, astronomers could catch these rare occurrences and estimate how many hidden objects existed. While some microlensing events were indeed detected, the numbers fell far short of what would be needed. Macros might exist in small quantities, but they couldn't possibly account for the vast missing mass that observations demanded. Cold gas clouds presented another possibility. Perhaps enormous quantities of hydrogen drifted invisibly through space, too cool and diffuse to emit detectable light, but gas clouds aren't completely invisible. They absorb background starlight at characteristic wavelengths and emit faint radio signals. Comprehensive surveys found nowhere near enough gas to solve the mystery. Cosmic dust, while capable of blocking light dramatically, also proved insufficient. Dust grains are made of ordinary atoms, heavy elements forged in stellar cores and blown into space. They leave distinctive signatures when they absorb and re-emit radiation. The required quantities simply weren't there. Each negative result made the conclusion more inescapable. The bulk of dark matter isn't stars, isn't gas, isn't dust. It isn't made of ordinary atomic matter at all. It represents something entirely new, invisible to electromagnetic radiation, but still exerting gravitational influence on cosmic scales. This realization opened up fascinating connections to particle physics. If dark matter consists of previously unknown particles, then the standard model of particle physics, successful as it's been, must be incomplete. Physicists began proposing exotic candidates that could fill this role. WIMPs, weakly interacting massive particles, became one of the leading possibilities. These hypothetical particles would have substantial mass, providing the gravity needed to explain galactic behavior, but would interact only through the weak nuclear force. This would make them essentially invisible to light, while still allowing them to clump into the massive halos that observations require. Axions represent another intriguing candidate. Originally proposed to solve an unrelated problem in quantum field theory, these lightweight particles could exist in truly enormous numbers. Their interactions with ordinary matter would be so feeble that they could pass through entire planets without leaving a trace. Stereo neutrinos offer yet another possibility. Related to the ghostly neutrinos that stream constantly through our bodies, these heavier cousins would interact even more weakly with ordinary matter. They could account for dark matter while remaining effectively undetectable by conventional means. What all these candidates share is their fundamental alienness. They're not constructed from the protons, neutrons, and electrons that build the familiar world. They represent entirely new categories of matter, operating by different rules, making up most of the universe while remaining hidden from direct observation. The search for these particles has spawned remarkable experiments. Deep underground laboratories shield sensitive detectors from cosmic radiation, hoping to catch the rare collision of a dark matter particle with ordinary atoms. Particle accelerators smash protons together at incredible energies, looking for signs that dark matter particles might be created and detected. So far, these searches haven't definitively identified any dark matter candidate, but the absence of direct detection doesn't diminish the evidence for dark matter's existence. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, all continue to point toward the same conclusion. The mass is real, even if we can't yet say exactly what it is. There's something almost poetic about this situation. For most of human history, stars represented the very essence of cosmic matter. They were the obvious inhabitants of space, the natural symbols of existence itself. Ancient cultures built entire mythologies around these points of light, seeing in them the fundamental forces that shaped reality. To discover that stars are actually a small minority, that the true majority consists of something completely invisible and unknown, forces us to reconsider our place in the cosmic order. The night sky that seems so rich and full actually shows us only the surface of a much deeper reality. This doesn't diminish the importance of stars and the ordinary matter they represent. Stars remain the crucibles where heavy elements are forged, the energy sources that power planetary systems, the beacons that allow galaxies to announce their presence across cosmic distances. Life as we know it depends entirely on stellar processes and the chemistry they enable. But stars are no longer the whole story. They're brilliant islands floating in a vast ocean of something else, something that shapes the universe's structure while remaining forever beyond our direct perception. It's a reminder of how much mystery still surrounds us, even in an age when we sometimes feel that science has mapped most of reality's important features. The particles we know about, the ones that make up everything we can touch and see, represent just a tiny fraction of what's actually out there. It's a humbling thought, really, that the universe we experience so directly is more like a collection of decorations scattered across something much vaster and more mysterious. When we gaze up at the night sky, those brilliant points of light grab our attention immediately. They seem so important, so central to everything. But they're actually more like landmarks, marking the edges and curves of invisible structures that dwarf them completely. The stars might be beautiful, but they're not running the show. Think about our own galaxy for a moment. The Milky Way stretches across the darkness like a river of light, containing billions upon billions of stars, each one potentially hosting worlds of its own. Yet wrapped around all of that visible splendor is something 10 times more massive, something we can't see at all. This invisible scaffold is what actually holds everything together. Without it, the galaxy would simply fall apart, and none of us would exist. This invisible mass reveals itself only through its gravitational pull. It shapes galaxies, binds enormous clusters of stars together, and weaves what astronomers call the cosmic web. But gravity alone doesn't tell us what this mysterious substance actually is. It's not made of stars, not composed of gas or dust, not built from the familiar atoms that form our bodies and our world. So scientists began to imagine. They started proposing particles that have never been detected, particles that might fill the universe while slipping past us completely unnoticed. This might sound like wild speculation, but it's actually how physics often works. Many particles were predicted long before anyone actually found them. Take neutrinos, for example. Back in the 1930s, scientists noticed that energy seemed to be disappearing during certain types of radioactive decay. Someone suggested that maybe an invisible particle was carrying that energy away. It seemed desperate at the time, almost like making something up, but decades later, neutrinos were finally detected, and now they're a fundamental part of our understanding of physics. The Higgs boson followed a similar path, predicted in the 1960s, finally confirmed in 2012. The history of physics is filled with these stories, where theory points towards something long before experiments can actually reveal it. One of the leading candidates for dark matter goes by the name WIMP. That stands for Weakly Interacting Massive Particle, which pretty much describes what it would need to be. Heavy enough to create the gravitational effects we observe, but interacting so weakly with ordinary matter that it doesn't emit or absorb light. That's why we can't see it directly. These particles could have formed in enormous numbers during the early universe, when conditions were far more extreme than anything we see today. The predicted abundance of WIMPs happens to match the amount of dark matter astronomers observe throughout the cosmos. This coincidence has been called the WIMP miracle, and it makes these particles particularly attractive to researchers. For decades now, enormous experiments have been designed to catch just one of these elusive particles colliding with ordinary matter. The detectors are buried deep underground, shielded from cosmic rays and background interference. They're often filled with noble gases, like xenon or argon, substances that would produce faint flashes of light if struck by a WIMP. So far, no definitive signal has been found, but the sensitivity keeps improving with each new generation of detectors. Each failed detection actually provides valuable information, ruling out more possibilities and narrowing the search. Another candidate goes by the name Axion. These would be incredibly light particles, perhaps 1 trillion times lighter than an electron. They were originally proposed to solve a completely different problem in quantum physics. But their properties also make them good dark matter candidates. If axions exist, they could be produced in vast numbers, forming a cold, invisible background throughout space. Unlike WIMPs, they wouldn't be massive individual particles. Instead, their sheer abundance could account for all that missing mass. Experiments searching for axions use sensitive instruments designed to detect faint electromagnetic signals. The idea is that axions might produce detectable radiation when exposed to strong magnetic fields, like WIMPs. Axions remain hypothetical, but they're taken seriously as a possible explanation. Then there are sterile neutrinos. Regular neutrinos are already strange enough, light and ghostly particles that stream through matter almost without interacting at all. Trillions of them pass through your body every second without having any effect whatsoever. But the neutrinos we know about have too little mass to account for dark matter. A heavier cousin, one that interacts even less than ordinary neutrinos, could potentially exist. These sterile neutrinos would be invisible in most experiments, but they might leave subtle imprints in the structure of the cosmos. Some observations of X-rays from distant galaxies have hinted at possible signals, though nothing conclusive has been confirmed yet. Some theories go even further. They suggest that dark matter might not be just one type of particle, but an entire hidden sector of physics. Just as ordinary matter includes protons, neutrons, electrons, and many others, dark matter could have its own rich complexity. There might be dark photons, dark forces, even dark atoms, all interacting with one another while remaining mostly invisible to us. If this is true, then we're not just missing a single particle, but an entire shadow version of physics that coexists with everything we can see. The search for these unseen particles spans many different approaches. Particle accelerators like the Large Hadron Collider look for signs of new particles produced in high-energy collisions. If energy and momentum seem to vanish from the aftermath of a collision, it could mean a dark matter particle slipped away undetected. Underground detectors sit in patient silence, waiting for that rare interaction between dark and ordinary matter. These experiments are often located beneath mountains or deep in mines, massive tanks of liquid xenon or argon standing ready to catch the faintest flash or vibration. Each time no signal is found, the parameter space shrinks a little more, guiding the design of the next generation of detectors. It's a process of elimination that gradually closes in on the truth. Astronomical observations provide yet another angle. If dark matter particles can occasionally destroy each other through annihilation, they might produce gamma rays or other detectable signals. Telescopes scan the skies, particularly focusing on the centers of galaxies where dark matter should be densest, looking for unusual excesses of radiation. A few intriguing hints have emerged over the years, but none have yet reached the level of definitive discovery. The search continues, driven by the knowledge that we're missing something fundamental about the universe we inhabit. The hunt for invisible particles that fill our universe happens in the strangest places you might imagine. While you picture astronomers on mountaintops with giant telescopes, some of the most important discoveries might come from deep underground, in laboratories carved into mountains and abandoned mines. Scientists descend thousands of feet below the surface, not to escape the world, but to find the hidden majority that surrounds us every day. The reason for going so deep underground is actually quite simple. Our planet gets constantly hit by cosmic rays, high-energy particles, shooting down from space. These create a shower of secondary particles that rain down on us all the time. If you're trying to catch something that barely interacts with anything, you can't have all this cosmic noise interfering. Rock becomes your shield. The deeper you go, the quieter it gets. In these underground caverns, massive detectors wait in silence. Many use noble gases like xenon or argon, cooled down until they become liquids. These liquids are incredibly pure, chemically stable. When a particle hits an atom in the liquid, it might produce a tiny flash of light, maybe a faint electrical signal. Thousands of sensors surround these liquid chambers, ready to catch even the smallest whisper. Deep beneath the Gran Sasso mountain in Italy, One experiment, called Xenon, sits patiently. Its latest version contains several tons of liquid xenon inside a huge tank. Everything is kept at precisely controlled temperatures, shielded from any background radiation. For years now, this detector records flashes of light. Most come from ordinary particles, natural radioactivity, background noise. But scientists carefully examine every single event, looking for something that doesn't fit the usual patterns. Another major experiment, Zeppelin, operates in what used to be a gold mine in South Dakota. It uses an even larger detector, designed to be among the most sensitive in the world. We're talking about catching events so rare, they might happen only once per year in the entire massive chamber. The scale of patience required is almost philosophical. This willingness to wait years for a single meaningful signal. There's something profound about this approach to discovery. Scientists have created a global network of these underground watchtowers, silent and patient, waiting for invisible particles to announce themselves. Experiments in China, Canada, Italy, all part of this coordinated effort to listen for the faintest signals from the hidden universe. The particles they're hunting make up most of the universe, yet they drift through us constantly without our awareness. Every second, countless dark matter particles might be passing through your body, through the walls around you, through the entire planet, barely interacting with anything. They hold galaxies together, shape the cosmic web, outweigh all the stars combined, yet they remain completely beyond our normal senses. What makes this search even more remarkable is that so far, no experiment has made a definitive detection. This might sound like failure, but in science, even silence tells us something important. Every null result narrows down the possibilities, rules out certain ranges of mass and interaction strength. Over the years, the space where these particles could be hiding has grown smaller and smaller. The classic candidates, called WIMPs, have been the focus of many searches. Some once popular models have been excluded entirely, others remain possible. Each experiment pushes the limits further, becomes more sensitive, waits longer for that crucial signal. Part of the challenge is that dark matter might interact even less frequently than scientists originally hoped. There's a deeper lesson in this underground search. For all the progress humanity has made in understanding the cosmos, most of it remains hidden from us. The familiar matter we learned about in school, all the atoms and particles we know, represent only a small minority of what exists. The true majority belongs to particles we have never met. This realization is both humbling and hopeful. It means discovery still lies ahead of us. The universe isn't a solved puzzle, but a living mystery with pieces waiting to be uncovered. Every day, these underground detectors sit in darkness, ready to catch the first direct evidence of the invisible scaffolding that holds reality together. Some scientists have wondered if dark matter might not be particles at all. Perhaps our understanding of gravity itself is incomplete. What we attribute to unseen matter might actually reveal flaws in our equations. Modified theories of gravity, like something called MUND, try to alter the laws at large scales. But these alternatives struggle to explain all the evidence we see, especially complex phenomena like colliding galaxy clusters and patterns in the cosmic microwave background. Most physicists believe dark matter consists of real particles, just ones we haven't discovered yet. The debate itself reflects how deep this mystery runs. If these particles are finally found, the discovery would mark one of the greatest milestones in physics. We would finally know what most of the universe is made of, connecting the study of the largest structures with the smallest particles. Until then, the search continues in these quiet underground laboratories. Detectors wait in silence. Telescopes scan the sky above. Physicists refine their theories and propose new particles. The universe is patient, and science learns to be patient too. There's something almost meditative about this approach, this willingness to wait years or decades for nature to reveal its secrets. When you think about it, we live surrounded by an invisible reality. Particles that drift through us every moment without leaving a trace, shaping the cosmos in ways we're only beginning to understand. To know such a hidden majority exists is to see the limits of our perception. To search for it is to extend those limits, reaching into the unknown with remarkable persistence and imagination. Deep beneath mountains around the world, scientists have carved out sanctuaries of silence. These underground laboratories exist in a state of perpetual waiting, listening for whispers from the invisible universe that surrounds us. The patience required for this work defies our modern expectations of instant results. Dark matter, if it exists as particles, might be streaming through everything right now, through the rock above these detectors, through the equipment itself, through the bodies of the researchers who tend to these machines. The profound reality is that we wouldn't need to create dark matter, only learn to notice it passing by. These detection systems rely on the most delicate measurements imaginable. A single particle interaction could produce just a tiny flash of light or cause a crystal to vibrate almost imperceptibly. The challenge becomes separating genuine signals from the countless sources of background noise that plague any sensitive instrument. Some experiments use liquid xenon, others prefer argon, each cooled to temperatures that would freeze the air around us solid. These noble gases become the medium through which we hope to glimpse the unseeable. When a dark matter particle strikes a nucleus in the liquid, it should produce both light and electrical signals that sophisticated sensors can detect. The underground setting serves a crucial purpose beyond just blocking cosmic rays. It creates an atmosphere that feels almost sacred, these enormous tanks gleaming with instruments, surrounded by layers of shielding that protect against every possible source of interference. Scientists have essentially built temples to the unknown, places where humanity reaches toward mysteries that dwarf our everyday experience. But liquid detectors represent just one approach to this cosmic puzzle. Cryogenic crystals, cooled to nearly absolute zero, can sense the tiniest vibrations when a particle collision occurs. The crystal lattice itself becomes a detector, transmitting energy through its structure in ways that sensitive instruments can measure. Bubble chambers offer yet another technique, using superheated liquids that remain stable until disturbed. A single particle interaction can trigger the formation of a visible bubble, providing direct visual evidence of something that would otherwise remain completely hidden from our senses. The diversity of these approaches reflects something profound about the scientific method. No single experiment can definitively answer whether dark matter particles exist and what their properties might be. Instead, researchers cast a wide net, using different techniques that each have unique advantages and limitations. Years pass as these detectors accumulate data, their electronic systems faithfully recording every event that meets their triggering criteria. Teams of scientists analyze this information, searching for patterns that might indicate genuine dark matter interactions, rather than more mundane background events. Occasionally, tantalizing hints emerge from this careful analysis. The Dama experiment in Italy has reported signals that vary with the seasons, potentially explained by Earth's changing motion through a sea of dark matter as our planet orbits the Sun. But other experiments have failed to confirm these results, leaving the scientific community in ongoing debate about their meaning. Such episodes illustrate how delicate this entire enterprise really is. The distinction between signal and noise can be extraordinarily subtle, requiring years of data collection and careful analysis before any definitive conclusions become possible. The underground laboratories embody a particular kind of scientific humility, rather than trying to force nature to reveal its secrets through high-energy collisions. These experiments acknowledge that the universe might already be showing us what we need to see, if only we learn how to look properly. This approach requires a fundamentally different mindset from other areas of physics. Instead of creating extreme conditions to probe matter's deepest properties, researchers must perfect the art of listening, developing ever more sensitive instruments capable of detecting the faintest possible interactions. The scale of these projects reflects humanity's commitment to understanding our place in a universe that remains largely mysterious. We excavate laboratories deep underground, construct detection systems that cost hundreds of millions of dollars, then wait patiently for phenomena that might never occur within our lifetimes. Even if these experiments never directly detect dark matter particles, they serve an important function in constraining theoretical possibilities. Each negative result eliminates certain ranges of particle masses and interaction strengths, gradually narrowing the parameter space where dark matter might hide. The philosophical implications run deeper than just particle physics. These underground searches represent our species grappling with the limits of direct sensory experience. Most of the universe apparently consists of substances that don't interact with light, making them invisible to our eyes and most conventional instruments. Yet we persist in trying to extend our perception beyond these natural boundaries. The underground detectors become extensions of human consciousness, reaching toward realities that evolution never equipped us to sense directly. Meanwhile, on the surface world above these laboratories, galaxies continue their ancient dance through space, held together by the gravitational influence of matter we cannot see. The cosmic web stretches across billions of light years, its structure determined primarily by dark matter's distribution, rather than the familiar atoms that make up stars, planets, and ourselves. This creates a strange dichotomy in our understanding of existence. The matter we know intimately, the substances that compose our bodies and everything we directly experience, represents only a small fraction of cosmic reality. We find ourselves as conscious observers embedded in a universe dominated by phenomena that remain essentially alien to our everyday experience. The underground search for dark matter particles represents one of our most ambitious attempts to bridge this gap between the seen and unseen. Success would fundamentally transform our understanding of matter itself, confirming that entire categories of particles exist beyond those described by current theories. But failure would be equally significant, forcing theoretical physicists to reconsider basic assumptions about dark matter's nature. Perhaps it consists of something far stranger than conventional particles, requiring entirely different detection strategies that we haven't yet imagined. The quiet chambers beneath the Earth continue their vigil regardless of these uncertainties. Electronic systems faithfully monitor their detector rays, scientists analyze incoming data streams, and the universe keeps its secrets while we slowly refine our questions about its deepest nature. When particle physicists fire up their massive colliders, they're creating conditions that haven't existed since moments after the Big Bang. These machines smash protons together at incredible speeds, and in those brief collisions, energy transforms into matter in ways that mirror the birth of the universe itself. It's almost poetic, really, how we've learned to recreate cosmic violence in underground tunnels, searching for particles that might make up most of reality. The Large Hadron Collider sits quietly beneath the border of France and Switzerland, its silence between experiments somehow more profound than its roaring operations. When it runs, it's looking for something that might not even want to be found. Dark matter particles, if they exist in the energy ranges we can probe, seem determined to stay hidden. Each collision produces a shower of familiar particles, but what scientists really want to see is what's missing, the energy that vanishes without explanation. The absence of detection isn't failure, though, it's information. Every negative result draws boundaries around where dark matter might be hiding. The Tevatron in America contributed to this map of possibilities before it shut down. The European machine called L did the same before the LHC took its place. Smaller colliders around the world have added their own pieces to this puzzle of elimination. Together, they've ruled out vast territories where dark matter could have been lurking. Underground detectors work in perfect partnership with these colliders, listening for the faint whispers of dark matter particles bumping into ordinary atoms. While colliders try to create dark matter from pure energy, these buried laboratories wait patiently for dark matter to reveal itself through rare interactions. It's like having two different conversations with the same invisible entity, hoping one approach might finally get an answer. But the universe itself provides the most spectacular laboratory of all. Supernovas explode with energies that dwarf our most powerful machines. Black holes devour matter and spit out jets of particles across millions of light years. When entire galaxies collide, the gravitational forces involved reshape space itself. If dark matter particles can destroy each other in these cosmic furnaces, they might produce gamma rays we can detect. Satellites scan the sky constantly, looking for unusual glows that don't match any known sources. There's been a mysterious excess of gamma rays coming from the center of our galaxy, a signal that some scientists think might be the signature of dark matter annihilation. But like so many hints in this field, it remains tantalizingly ambiguous, neither confirmed nor dismissed. Cosmic rays tell their own story. These high-energy particles, accelerated by processes we can barely imagine, rain down on Earth constantly. Some carry energies that exceed anything our colliders can produce. If dark matter interactions are creating unusual numbers of certain particles, experiments mounted on the International Space Station might notice the excess. Again, there have been intriguing hints, patterns that don't quite fit the expected background, but nothing definitive enough to claim victory. The cosmos teases us, just like the colliders do. Every method of detection seems to find suggestions, anomalies that could be dark matter, but could also be something more mundane. It's as if reality is playing an elaborate game of hide and seek, leaving just enough clues to keep us searching, but never enough to satisfy our curiosity. Completely, this combination of approaches reflects something deeper about how we understand the universe. No single method can answer such fundamental questions. Underground detectors, particle colliders, and space telescopes each probe different aspects of the same mystery. They inform each other, strengthen each other's conclusions, and together they form a comprehensive net designed to catch evidence from whatever direction it might come. The persistence of this search reveals just how important the question really is. We're not chasing some minor detail of physics. We're trying to understand what most of the universe is actually made of. When you consider that ordinary matter, everything we can see and touch, represents less than 5% of cosmic inventory, the stakes become clear. We're essentially blind to 95% of reality. Imagine what discovery would actually feel like in any of these settings. In a collider, it might start as a pattern in the data. Collisions that consistently show missing energy in ways that can't be explained by known physics. The realization would probably come gradually, as statisticians become more and more confident that they're seeing something real rather than random fluctuations. In an underground laboratory, discovery might announce itself as a signal rising steadily above the background noise of cosmic rays and radioactive decay. Day after day, week after week, the detectors would register impacts that match the theoretical predictions for dark matter interactions. The signal would be undeniable, repeatable, transformative. From space, the revelation might come as an unexpected spectrum of light, gamma rays with energies and patterns that perfectly match what theorists have predicted for dark matter annihilation. Telescopes might spot a glow in regions where dark matter should be densest, a cosmic signature written in high-energy photons. Any one of these discoveries would reshape physics completely. Not just by confirming that dark matter exists, but by opening entirely new fields of research. We'd suddenly have a new fundamental particle to study, new forces to understand, new questions to ask about the nature of reality itself. The parallels between human engineering and cosmic processes are striking when you think about it. Colliders create extreme conditions through careful design and tremendous energy investment. The universe creates similar conditions naturally through the violence of stellar collapse, the merger of neutron stars, the collision of galaxy clusters. Both environments produce showers of exotic particles. Both might be manufacturing dark matter or providing conditions where dark matter reveals its presence. There's something almost philosophical about this dual approach to discovery. We search for truth both by recreating cosmic conditions in our laboratories and by observing cosmic conditions directly through our telescopes. It's as if we're having two different conversations with the universe, one conducted through experimentation, the other through observation, both asking the same fundamental question about what reality contains. This reflects a larger truth about scientific understanding. Knowledge emerges not from any single method, but from the interplay between many different approaches. Data from particle colliders help set parameters for underground searches. Results from space telescopes constrain the theories that guide collider experiments. Each piece of evidence strengthens the others, creating a web of understanding that's more robust than any individual measurement. The search for dark matter isn't really separate efforts happening in parallel. It's a single, interconnected global pursuit, with different tools examining the same mystery from complementary angles. Physicists in underground laboratories coordinate with astronomers operating space telescopes. Theorists who work on collider physics collaborate with cosmologists who study galaxy formation. The boundaries between these fields have blurred in the pursuit of this particular truth. As of right now, the particles remain completely elusive. We haven't met them directly, haven't captured them, haven't definitively proven they exist, but the circumstantial evidence continues to accumulate from every direction, from the rotation curves of galaxies to the cosmic microwave background radiation, from computer simulations of structure formation to gravitational lensing observations. The case grows stronger, even as the particles themselves stay hidden. The absence of direct detection has become a clue in itself, pushing theoretical physicists to broaden their thinking beyond the conventional candidates. Maybe dark matter isn't the type of particle everyone expected. Maybe it's much lighter than predicted, or much heavier. Maybe it interacts through forces we haven't considered, or maybe it doesn't interact with ordinary matter at all, except through gravity. Some scientists now propose that dark matter might be ultralight particles with wave-like properties, forming a kind of invisible field that permeates all of space. Others suggest it might be composite, made of bound states similar to protons and neutrons, but existing in a completely separate sector of reality. Still others explore whether primordial black holes, formed in the earliest moments after the Big Bang, might account for at least some of the missing mass. The story continues to evolve, driven forward by the silence of underground detectors, the roaring collisions in particle accelerators, the quiet glow of gamma rays detected by orbiting telescopes, and the invisible architecture of the cosmic web itself. Every measurement, whether it detects something or detects nothing, adds information to our understanding. The search is as much about refining our questions as it is about finding definitive answers. When astronomers started measuring how fast distant galaxies were moving away from us, they expected to find the universe slowing down. Gravity should be putting the brakes on cosmic expansion, after all, but the data told a completely different story. The universe wasn't slowing down at all, it was speeding up. Something invisible was pushing everything apart, faster and faster. This mysterious force got the name dark energy, and it turns out to be everywhere. When scientists add up everything in the universe, dark energy makes up about 68% of the total. Dark matter accounts for another 27%. All the stuff we can actually see, stars, planets, gas clouds, even black holes, that's only 5% of everything that exists. Think about that for a moment. 95% of reality is completely invisible to us. We're living in a universe where almost everything is hidden from our senses. It's like trying to understand a vast symphony when you can only hear 5% of the instruments playing. Dark matter and dark energy couldn't be more different from each other, though. Dark matter acts like regular matter in some ways. It has mass, it clumps together, it pulls things toward itself with gravity. Dark matter is what holds galaxies together, keeps them from spinning apart. Without it, the stars in our galaxy would just fly off in all directions. Dark energy does the exact opposite. It doesn't clump anywhere, it's spread out perfectly smooth throughout space. And instead of pulling things together, it pushes them apart. It's like the universe has two competing forces, one trying to build structures, the other trying to tear them apart. The cosmic microwave background, that ancient light from when the universe first became transparent, shows us this cosmic tug-of-war in action. The tiny ripples in that light carry the fingerprints of both dark matter and dark energy working together in the early universe. Here's where things get really puzzling, though. The balance between these two forces seems almost perfectly fine-tuned. If dark energy had been much stronger in the past, galaxies never would have formed. If it had been weaker, the universe might have already collapsed back on itself. The fact that we exist at all suggests the cosmic recipe had to be just right. Scientists call this the cosmic coincidence problem. Why do we happen to live at exactly the time when dark energy started taking over. For billions of years, dark matter was winning the battle, allowing structure to form. Only recently, in cosmic terms, did dark energy become dominant. The timing seems remarkably convenient for life to exist. This balance determines our ultimate fate too. If dark energy keeps getting stronger, the expansion will accelerate forever. Galaxies will drift so far apart, they'll disappear from each other's view. Stars will burn out one by one, leaving behind a cold, empty universe. Some call this scenario the heat death of the cosmos, but there's an even more dramatic possibility. If dark energy grows too powerful, it could eventually overcome all the other forces. First, it would pull galaxy clusters apart, then individual galaxies, then solar systems, then planets, and finally even atoms themselves. Scientists call this the Big Rip, where the very fabric of space expands so fast it tears matter apart. Of course, we don't really know what dark energy is yet. It might be related to something Einstein once considered a cosmological constant built into space itself. Or it could be something completely new, a field we've never encountered before, or even a sign that our understanding of physics breaks down on cosmic scales. The search for dark matter particles continues in laboratories deep underground, where detectors wait patiently for one of these invisible particles to bump into an atom. So far, nothing definitive. Dark matter seems to interact with regular matter only through gravity, making it incredibly difficult to catch. Meanwhile, new telescopes and surveys are mapping how dark energy affects the growth of structure across billions of light years. Each measurement helps narrow down the possibilities, bringing us closer to understanding what makes up most of our universe. There's something deeply humbling about living in a time when we know these mysteries exist, but can't yet solve them. For most of human history, people looked up at the night sky and thought they were seeing everything there was to see. Now we know the visible universe is just a tiny fraction of what's really out there. We evolved to trust our senses, to believe that seeing is understanding. But the cosmos has revealed that most of reality exists beyond the reach of our eyes and instruments. We can measure the effects of dark matter and dark energy with incredible precision, but the substances themselves remain elusive. In a strange way, though, these invisible forces connect us to the deepest workings of the universe. Dark matter helped shape the cosmic web that galaxies hang on like dewdrops on a spider's web. Dark energy determines whether the universe expands forever or eventually contracts. These unseen influences guided the formation of everything we know. Without dark matter's gravitational scaffolding, the gas that would become our solar system never would have collected in the right place. Without dark energy's push, the universe might have recollapsed before stars had time to forge the heavy elements that make planets and life possible. So we find ourselves as luminous beings in a largely dark universe, made of atoms that represent just a small fraction of what exists. The main story of cosmic evolution belongs to things we cannot see or touch. Yet somehow, in ways we're only beginning to understand, that invisible majority has made our existence possible. The universe keeps most of its secrets hidden, but it has given us the tools to detect those secrets indirectly. We may not be able to hold dark matter in our hands or see dark energy directly, but we can map their influences across space and time. Our understanding remains incomplete, but it's growing deeper with each new observation. Curiosity drives us forward into the unknown. This restless need to understand, to question, to explore, it shapes every step we take into the cosmos. The universe keeps revealing itself as larger, stranger, more mysterious than we ever imagined. Each discovery shows us just how much more there is to learn. For decades, scientists have assumed gravity works exactly as we understand it. Newton gave us elegant equations centuries ago. Einstein later refined them with general relativity. These theories describe how matter attracts matter, how planets orbit stars, how stars gather into galaxies. They explain how galaxies themselves curve the fabric of space-time. In this picture, we need dark matter, because gravity acting on visible matter alone, it doesn't account for the motions we see, But what if that assumption is wrong? What if the fault lies not in missing matter, but in gravity itself? Could it be that the force we thought we knew so well is actually incomplete? This possibility has both fascinated and troubled scientists for decades. The evidence for unseen mass seems overwhelming. Galaxies spin too fast, clusters bind too tightly. Light bends more than expected, but all of that evidence, it assumes gravity behaves exactly as Einstein's equations predict. If gravity acts differently on cosmic scales, then maybe we don't need to invent unseen particles at all. Maybe what we're seeing isn't missing matter, but a deeper truth about the force that governs everything. The most famous alternative goes by the name modified Newtonian dynamics. Scientists call it MUNDI for short. A physicist named Mordechai Milgrom proposed it back in the 1980s. Monde suggests that Newton's law of gravity works as expected at high accelerations, like here in our solar system. But it changes at extremely low accelerations, the kind experienced by stars at the edges of galaxies. In this regime, gravity doesn't weaken as quickly with distance. As Newton's law predicts, the result is that galaxies can rotate with flat curves, without needing dark matter halos at all. MOND was designed specifically to explain galactic rotation curves. In many cases, it works remarkably well. But MOND alone, it's not enough. When applied to galaxy clusters, it struggles. The motions of galaxies within clusters, the hot gas bound to them, they still require additional unseen mass, even under modified gravity. MOND also has difficulty explaining the cosmic microwave background. Those patterns align neatly with dark matter, but not with simple modifications of gravity. To address these issues, scientists have developed extensions of MOND. They incorporate elements of relativity, but challenges remain. There's also another class of theories that involves more general modifications to Einstein's relativity itself. These approaches fall under the broad heading of alternative gravity theories. Some include scalar tensor theories, others something called F of R gravity. Some of these models introduce completely new fields, others change how space-time curvature responds to energy and matter. Some attempt to unify dark matter and dark energy into a single modification of gravity. The goal is ambitious, to explain both the clustering of galaxies and the accelerating expansion, without invoking invisible substances. So far, none of these theories has achieved the same level of success across all observations as the standard model, with dark matter and dark energy. Dark matter, though mysterious, provides a simple, consistent explanation for galaxy rotation, gravitational lensing, the cosmic microwave background, large-scale structure, and cluster dynamics. Modified gravity theories often explain one or two of these phenomena well, but they falter on the others. Still, the fact that such alternatives are pursued, it's a sign of healthy science. Questioning the foundations, that's part of progress. It's not unprecedented for physics to revise its understanding of fundamental forces. Newton's laws worked beautifully for centuries, until relativity showed they were only an approximation. Relativity itself may one day be revised by a deeper theory, one that incorporates quantum mechanics properly. In this sense, asking whether gravity is wrong, it's not outlandish but natural. It's part of the ongoing refinement of our picture of the universe. The possibility that gravity could be incomplete, it also touches on profound philosophical questions. If dark matter doesn't exist, and what we're really observing is a flaw in our equations, then much of the effort to find particles would be misdirected. It would mean that the unseen majority of the universe isn't matter at all. It would be a reflection of our own misunderstanding. That's both humbling and unsettling. It reminds us that science is provisional, that even the most trusted ideas can be questioned, challenged, overturned. At the same time, the search for dark matter particles, it's not wasted effort. Even if gravity turns out to be the issue, every experiment, every particle collider, every cosmic survey contributes knowledge. The act of looking tests our theories, it sharpens our tools, pushes technology forward. Whether the answer is new matter or new gravity, the pursuit itself advances science. One of the strongest counter-arguments to modified gravity comes from something called the bullet cluster. It's a colliding system of two galaxy clusters. The visible hot gas lags behind, while gravitational lensing shows the bulk of the mass aligned with the galaxies. This separation is difficult to explain with modified gravity alone. It strongly suggests that some form of invisible matter is present, passing through without interacting like gas does. Modified gravity struggles here, while dark matter provides a straightforward explanation. Still, Mendine and other theories maintain a following, particularly because of their elegance in explaining galactic rotation curves without invoking unseen halos. They serve as a reminder that we shouldn't accept invisible particles too easily, not without proof. Until dark matter is detected directly, skepticism remains valuable. Modified gravity may not solve the puzzle completely, but it keeps the conversation alive. It pushes theorists to consider possibilities beyond the obvious. There's also the tantalizing chance that the truth is more complex, that both dark matter and modified gravity are part of the picture. Perhaps unseen particles do exist, but gravity also behaves differently than we think. The universe has a way of being more subtle, more intricate than our theories suggest. Every time we think we have it figured out, new mysteries emerge. That's what makes this journey so compelling, so endlessly fascinating. Gravity might be telling us lies. That's a thought that keeps some scientists awake at night. What if everything we think we know about how massive objects pull on each other? What if it's just incomplete? The idea sounds radical, but it's not impossible. Maybe dark energy isn't some mysterious force pushing the cosmos apart. Maybe it's just gravity behaving differently than we expect when things get really, really big. The evidence for dark matter being actual matter, actual particles floating around, it's still pretty strong. Most scientists lean that way, but the beautiful thing about science, the thing that makes it trustworthy, is that it's willing to question itself. Even when most people agree on something, there's always room to ask, what if we're wrong? What if gravity itself needs an update? This isn't just about particles or forces. It's about how we handle not knowing. Science has to balance evidence with skepticism, imagination with caution. The dark matter debate shows us how that works in real time. For centuries, gravity was invisible too. Newton could describe what it did, but he couldn't tell you what it actually was. Einstein gave us a better picture, showed us that massive objects bend space-time itself, but even that bending, you can't see it directly. You only see its effects. Dark matter and dark energy, they're just the newest chapters in this old story about how reality likes to hide behind what we can observe. Whether these invisible things are particles or signs that physics needs revision, they're expanding what we think the universe can be. They're reminding us that appearances, well, they're often deceiving. If dark matter is real, if it's actually there, then some truly strange objects might exist out there. Imagine a galaxy with no stars, just dark matter, sitting in space, massive but completely dark. These aren't science fiction. They're predicted by our best simulations of how the universe grows and changes. Not every clump of dark matter succeeds in making stars. Some fail to pull in enough gas. Some never light up at all. They just sit there, invisible skeletons without any flesh of starlight on them. For years, these objects existed only in computer models. But slowly, astronomers started finding hints that they might be real. The first clues came from dwarf galaxies, those tiny companions that orbit bigger systems like our Milky Way. Some of these dwarfs are incredibly faint. They have maybe a few million stars, compared to our galaxy's hundreds of billions. But when you measure how fast their stars move, you discover something odd. These little galaxies are almost entirely made of dark matter. The visible stars are just a tiny frosting on a much larger, invisible cake. In 2012, astronomers found something even stranger, a cloud of hydrogen gas in the Virgo cluster, spinning like a galaxy, but with no stars visible at all, just gas and dark matter, rotating together in the darkness. It was one of the first real candidates for a true dark galaxy. Since then, more weird objects have turned up. Some galaxies that seem to have almost no dark matter at all, others that are nearly pure dark matter with barely any stars. These extremes show us that galaxy formation isn't uniform. Dark matter sets the stage, but what happens next depends on many things. How much gas falls in, whether explosions from dying stars blow the gas away, whether the neighborhood strips material off. Sometimes, the stars just never take hold. You're left with structures where darkness reigns. Gravitational lensing gives us more evidence. When light from distant galaxies gets bent by clusters of galaxies in front of them, sometimes the bending is stronger than the visible galaxies alone can explain. Something else is there, bending the light, something massive but invisible. Empty halos, drifting among the brighter systems like ghosts. These discoveries tell us something important about dark matter's identity. If halos form everywhere, at all different sizes, then dark matter particles must clump together efficiently. Whether dark matter is cold, moving slowly in the early universe, or warm or hot, that affects how many small halos you get. Cold dark matter makes lots of tiny halos. Warm dark matter would smooth some of them out. By counting how many faint galaxies we actually see, and comparing that to computer simulations, scientists can figure out what kind of dark matter particles we're dealing with. Dark galaxies aren't just curiosities. They're experiments that the universe has written for us, testing our ideas about invisible physics. There's something unsettling about dark galaxies. A galaxy without stars is completely invisible to the naked eye. You could never see it, no matter how good your vision. It's a reminder that the glowing cosmos we admire is just a tiny fraction of what's really out there. For every beautiful spiral galaxy in our photos, there might be others drifting silently nearby, just as massive but living in complete shadow. These hidden systems are as real as the Milky Way or Andromeda. They just happen to exist outside the reach of ordinary vision. It makes you wonder what else is out there, invisible but present. On the practical side, studying dark galaxies teaches us about galaxy formation in general. Why do some dark matter halos succeed in making stars while others fail? What's the minimum mass needed for gas to cool down and collapse into the first stars? How do feedback processes, winds from newborn stars, explosions from supernovae, jets from black holes, how do they shape the final outcome? These questions are central to understanding how the universe works. Dark galaxies give us a unique window into them. By studying where light fails to appear, we learn why it appears elsewhere. Dark galaxies might not just be small dwarf systems either. Computer simulations predict halos of all sizes, and not all of them need to host bright galaxies. Some might be as large as normal galaxies but remain nearly starless. Detecting massive dark galaxies is even harder, but their gravitational influence could eventually reveal them. As our techniques improve, we might map these hidden giants, adding entire new classes of objects to our cosmic inventory. Empty halos, those without any stars or gas at all, push the mystery even further. These structures are pure dark matter, invisible except for their gravity. You can't study them through starlight or gas emissions. Only their effects on nearby systems, or on background light, can betray their presence. To think that such objects might outnumber the galaxies we see, that's a mind-bending realization. The luminous universe is only the tip of the iceberg. The dark, empty halos beneath form the bulk. This reshapes our sense of cosmic beauty completely. For thousands of years, humans have admired the stars as the essence of the night sky. But the stars are just decorations on invisible scaffolding. The true structure lies beneath, in the halos and filaments that guide everything. The Milky Way itself is only glowing frosting on a much larger dark cake. To appreciate the universe fully, we have to learn to see with more than our eyes. We have to recognize the importance of what doesn't shine. It's tempting to think of dark galaxies as ghostly, haunting the cosmos with their absence of light. But they're not supernatural. They're natural consequences of physics. Expected outcomes of gravity acting on dark matter. They remind us that the cosmos doesn't revolve around visibility. Our senses are biased toward light, but the universe isn't obliged to cater to them. Reality is so much larger than perception. Dark galaxies and empty halos extend the mystery from visible systems into the completely unseen. They confirm that dark matter isn't just background presence, it's a primary architect of the cosmos. The galaxies we see are only one subset of the structures it creates. Many others remain hidden, waiting to be revealed by indirect methods. If most of the universe is invisible, what does that mean for our place in it? How do we live with the knowledge that the stars we admire are actually the minority, the exceptions, rather than the rule? It's strange to realize that after centuries of study, after mapping stars, after building telescopes that see across billions of light years, we still understand only a small fraction of the cosmos. For all our progress, what we know sits like a thin layer on the surface of something far deeper. The stars, planets, gas, and dust, all the luminous universe, it's only about 5% of what exists. The rest is dark matter and dark energy, unseen but dominant. This means most of reality is not only invisible to our eyes, it's still mysterious to our minds. The phrase, "a universe we barely know," that's not an exaggeration. Think about how much of astronomy's history has been tied to light. From Galileo's telescope to Hubble's observations, every discovery has been rooted in photons, particles of light traveling across space to reach us. We learned that stars are distant suns, that the universe is expanding, all through analyzing light. But now we understand that light traces only the minority of existence. We're like explorers charting the shoreline of a vast continent, aware that the interior is immense, but still untraveled. What we do know is largely indirect. We know dark matter is there because galaxies spin, as if it were. We know it's there because galaxy clusters hold together and light bends more strongly than visible mass allows. We know dark energy exists because the universe's expansion accelerates. But what are they really? We don't yet know. We measure effects, not causes. We map shadows, not sources. The dominant parts of the cosmos remain undefined. This raises an unsettling thought. If we're only aware of 5% of the universe in detail, then our most cherished ideas about cosmic structure, about evolution, about the ultimate fate of everything, they're built on partial knowledge. They may be broadly correct, but they're nowhere near complete. There's more, much more, beyond our current grasp. It's easy to think of science as a steady march of progress, each discovery adding certainty. But here, progress has revealed uncertainty. We once thought we knew the universe, at least in outline. Stars, planets, galaxies, governed by gravity and light. Now we know that most of it is hidden, and that what's hidden defines what's visible. This isn't a step backward, but it's a reminder that knowledge is always provisional. Each answer leads to deeper questions. To live in a universe we barely know is both a scientific fact and a philosophical challenge. It asks us to accept limits, to acknowledge that reality is larger than perception. It asks us to live with humility, knowing that the cosmos doesn't revolve around what's accessible to human senses. The stars we see are not the full story. They're only the glowing edge of a much greater mystery. But this realization isn't despairing. If anything, it's invigorating. It means discovery isn't finished. It means vast mysteries remain open, waiting for new ideas, new experiments, new generations of thinkers. The fact that 95% of the universe is unknown, that's not a failure. It's an invitation. Consider what this might mean for our sense of place. For thousands of years, people have looked at the night sky and seen it as complete. Myths' stories were written around the constellations. Navigation was guided by their positions. Time was kept by their motions. The stars were thought to be eternal, fixed, the ultimate background, but now we know that the true background is darker still, and that the stars are temporary, fragile, a brief light against a larger unknown. This changes how we see ourselves. We're not at the center, not the main event, but participants in a universe whose true nature is still hidden. Even our words show our uncertainty. Dark matter and dark energy are placeholders, names given not to explain, but to admit ignorance. They describe what we don't know while pointing to the effects we do observe. We're used to naming things with confidence, giving them clear definitions. Here, our names are admissions. We call them dark because we cannot see them, not because we understand them. This openness can be uncomfortable, but it's also honest. To say we barely know isn't weakness, it's strength. It shows that science doesn't pretend to have final answers when none exist. It shows a willingness to sit with mystery, to recognize that reality is richer than our current models. That humility is itself progress. What might the future hold? Perhaps in a decade or two, underground detectors will find the particles of dark matter, confirming that they're real and measurable. Perhaps particle colliders will produce them, revealing their properties. Perhaps telescopes will detect unmistakable signals from dark matter annihilations or decays. Or perhaps we'll find that our assumptions about matter and energy are incomplete, and that gravity itself requires major revision. Whatever the outcome, the journey will deepen our knowledge, even if it changes our fundamental assumptions. The phrase "barely know" also speaks to time. Human civilization has been practicing science for only a few centuries. Compared to the age of the universe, this is less than an instant. It's no wonder we know so little. The fact that we've learned as much as we have is actually remarkable. To go from thinking Earth was the center of the cosmos to recognizing that we live in a universe dominated by unseen components, all in a few hundred years, that's extraordinary. The gaps in our knowledge aren't failures. They're the natural result of being at the very beginning of the story. Living in a universe we barely know also has a personal dimension. When you look at the night sky, the stars you see are real, but they're not the majority. Around each one lies an invisible halo of dark matter. Between them stretches space, accelerated by dark energy. Even your own body isn't exempt. Dark matter particles may pass through you by the trillions each second, completely unnoticed. You're immersed in the unknown every moment, whether you realize it or not. There's something humbling in that, but also something comforting. It means mystery isn't far away or abstract. It's here now, surrounding you. The unknown isn't only in distant galaxies, it's in the very fabric of reality. To live with that awareness is to live in a larger world, one where wonder is always possible. The story of dark matter and dark energy isn't only about science. It's about perspective. It tells us that we're small, that our senses are limited, but also that we're capable of reaching beyond them. We've built tools that let us glimpse the invisible, measure the unmeasurable, and imagine the unimaginable. We may barely know the universe, but we do know that it's vast, mysterious, and worth exploring. To live in a universe where most of existence is invisible is to accept that we dwell among shadows. The galaxies we see, the stars we name, the planets we map, they're only fragments. They glow brightly, yes, but they're not the whole. Around and beneath them lies the unseen scaffolding of dark matter, holding everything together. Across the vast reaches of space stretches the push of dark energy, driving expansion faster with time. We walk through life, bathed in light, yet we're carried by what we cannot see. Living in the shadows isn't an exception. It's our natural condition. The phrase might sound unsettling, as if shadows imply ignorance or fear. But in this context, shadows aren't sinister. They're simply the reminder that reality is larger than perception. Just as a tree casts a shadow that reveals its shape, the universe's luminous structures cast shadows, in motion, in bending light, in cosmic history. These shadows aren't absence. They're evidence. To live in them is to be constantly surrounded by signs of something greater. Every person, every planet, every star is immersed in this unseen mass. Dark matter isn't far away. It's here, now, streaming through the earth, through our bodies, through the detectors, waiting quietly underground. Though we don't feel it, it's present, just as air surrounds us, unseen yet essential. Living in the shadows means recognizing that invisibility doesn't mean absence. The hidden can be just as real, just as important as the visible. It also means living with humility. For so much of history, humans believed the visible world was all there was. The sky was the final backdrop, the stars eternal, the cosmos complete. Now we know that was an illusion. The stars are the surface of a much deeper reality. The visible is the exception, the minority. This doesn't diminish its beauty, but it changes its meaning. The shadows aren't static. They shape our lives directly. Without dark matter, our galaxy wouldn't hold together. The sun wouldn't orbit safely within the Milky Way. Earth wouldn't orbit the sun. Without dark energy, the universe wouldn't be expanding as it is, and our cosmic history would be utterly different. These unseen forces aren't abstractions. They're the conditions of our existence. Living in the shadows isn't optional. It's the only way we exist at all. In daily life, it's easy to forget this. Shadows don't intrude. They're quiet. They don't demand attention. You can go through your entire life without thinking about dark matter or dark energy and still see stars rise, still feel the warmth of the sun, still marvel at the night sky. But beneath those experiences lies a deeper truth. The motions of the stars, the structure of the sky, the very possibility of galaxies all depend on what you cannot see. To live in the shadows is to live in a reality, whether you acknowledge it or not. There's a certain comfort in this perspective. It tells us that the unseen isn't to be feared, but embraced. It's part of the natural order. Just as we accept that Earth spins though we can't feel it, or that air carries life, though we can't see it, so too can we accept that dark matter and dark energy shape our world, even if they remain invisible. Shadows aren't enemies, they're companions. For science, living in the shadows is both challenge and gift. The challenge is obvious. It's harder to study what you can't see, harder to measure what doesn't interact with light. But the gift is that shadows invite discovery. They demand curiosity. They remind us there's always more to learn, always another layer beyond the obvious. The search for dark matter and dark energy isn't just about physics. It's about the human drive to reach beyond appearances. This has always been the case. The greatest advances in science often come from noticing what's missing, from recognizing gaps between expectation and observation. Neptune was discovered because Uranus didn't move as predicted. The neutrino was proposed because energy didn't add up in radioactive decay. The Higgs boson was sought because particles lacked a mechanism to explain their mass. In each case, the shadow revealed the substance. Dark matter and dark energy are the latest and largest examples. Their shadows stretch across the universe, telling us something more is there. Living in the shadows also reshapes our sense of beauty. For centuries, stars were admired as perfect, complete, the pinnacle of creation. Now we know they're not the whole, but this doesn't lessen their wonder. If anything, it deepens it. Stars are no longer symbols of completeness, but of contrast. Their glow is remarkable precisely because it shines against a backdrop of invisible mass and accelerating space. Their light is rare, fragile, temporary. The shadows give the light its meaning. On a more personal level, the idea of living in shadows connects to how we navigate life itself. Much of human existence is shaped by things unseen. Thoughts, emotions, relationships, histories. We know they're real, not because we see them directly, but because of their effects. Trust, love, memory, loss, none are visible, but all are powerful. In this way, dark matter and dark energy aren't entirely foreign. They remind us that unseen forces aren't unusual. They're fundamental. We live with them every day. The shadows also point forward. What we know now is incomplete. The very phrase dark matter is temporary, a placeholder for something we haven't yet defined. One day, perhaps, we'll discover the true nature of these unseen components, give them names beyond dark. Until then, we live in shadows, learning what we can from the patterns they cast. That's not a failure, it's the natural state of discovery. To live in the shadows is to live in a world where knowledge is growing but not yet complete. The universe remains partly hidden, partly revealed. Galaxies shine, but their motions point to invisible halos. The cosmic web stretches, but its strands are traced only by light bending through unseen mass. Expansion accelerates, but the cause is unknown energy. This is our reality. Luminous islands in a sea of shadows. When you step outside at night and look upward, the sky feels timeless. Stars shimmer in their quiet patterns. Planets drift along their paths. The faint arc of the Milky Way stretches across the dark. It's easy to believe that what you see is the whole story, that the glowing points and soft bands of light are all there is. For most of human history, that was enough. The stars were companions, constant and complete. But today, we know there's another presence above us, one we cannot see, yet one that outweighs all the brilliance combined. The night sky has a secret companion, and it's been there all along. This companion is dark matter. It doesn't twinkle or shine. It leaves no trace on our eyes or cameras, yet it's everywhere. Each star you see is wrapped in a halo of the unseen. The Milky Way itself, with its 100 billion stars, is only the glowing skin of a far larger body, cradled by an invisible sphere of mass that extends hundreds of thousands of light years beyond the luminous disk. Every step you take beneath the stars is taken within this companion's grasp. You may not notice it, but it's there, guiding the motions of stars, holding the galaxy together. Imagine the sky without it. Stars wouldn't trace their familiar spiral arms. The Milky Way wouldn't persist for billions of years. The sun might not even have a stable orbit to carry Earth around it. Without the secret companion, the universe would unravel. Galaxies we admire would scatter, their stars drifting away into emptiness. The constellations we name wouldn't exist. The light that comforts us wouldn't have formed. This unseen partner makes the luminous possible, yet its silence is profound. Dark matter has been with us since the beginning. Since the earliest fluctuations after the Big Bang, long before stars ignited or galaxies formed, it gathered, clumped, and pulled, preparing the scaffolding into which gas would fall, sparking the first starlight. It's been present at every stage of cosmic history, from the birth of galaxies to their graceful rotation today. Still, it remains hidden, refusing to reveal itself directly. It's the most faithful of companions, constant and patient, but it never steps into the light. To stand under the night sky with this knowledge is to feel a new kind of connection. You're not only looking at stars, you're looking through the shadow of halos, across filaments of dark matter that span unimaginable distances. Each galaxy you glimpse, even the faintest smudge in a telescope, sits inside an invisible cocoon. The companion isn't local, not confined to our Milky Way. It's universal, shaping every corner of the cosmos. The thought can be unsettling, but it can also be comforting. To know that the visible isn't the whole is to understand that reality is larger than appearances. The secret companion isn't hostile, it's supportive. It holds everything together. It's the reason the night sky exists in its familiar form, the reason galaxies endure, the reason we can stand here to wonder about them. The shadows above aren't emptiness, they're presence. This presence also carries a lesson. The most important parts of reality aren't always visible. Stars draw the eye, but the unseen carries the weight. The visible is only a surface, a signpost pointing to something deeper. The secret companion reminds us that what matters most isn't always what shines brightest. This is true in science, but it's also true in life. Much of what sustains us, memory, connection, trust, is invisible, felt through effects rather than direct sight. To live under a sky with a hidden companion is to live with that reminder. Even as we study it, the mystery remains. We give it names, dark matter, halos, particles, but these are placeholders, not explanations. We know what it does, but not what it is. The night sky companion keeps its identity secret, even as it shapes everything. Perhaps one day detectors underground will catch it, or colliders will produce it, or telescopes will reveal unmistakable signals. Perhaps one day we'll meet the particles themselves. Until then, the secret remains. Yet even without that final answer, the companion is real, its effects are undeniable, its fingerprints are everywhere. In the rotation of galaxies, in the bending of light, in the patterns of the cosmic web, in the history of expansion, it's not belief or speculation, it's evidence, consistent and overwhelming. The night sky may look familiar, but beneath it lies a deeper truth, supported by the weight of the unseen. There's a strange beauty in knowing this. Stars above aren't diminished by the presence of dark matter. If anything, they're enhanced. Their glow is framed by something larger, their order sustained by something stronger. To see stars is to see decoration on a deeper reality, one that gives them form and longevity. The night sky's secret companion makes the light more meaningful, because it shows that light is rare, fragile, and precious against the greater unseen. When you next look upward, remember that you're not only seeing stars, you're seeing the surface of a larger story, one written in shadows and silence. The constellations, the spirals, the faint galaxies, all are signs of the hidden companion that's been with us since the beginning. You may not see it, but you live within it. You walk, breathe, and wander inside its grasp. The universe will continue to expand, galaxies will drift farther apart, stars will burn out, and the night sky will change. But the secret companion will remain, shaping what it can, holding what it must, silent and unseen. Living beneath it, we're reminded that mystery isn't the absence of knowledge, but the presence of something greater than we yet understand. The story of dark matter, from its first hints to the cosmic web it weaves, is still unfolding. But even now, even before its particles are named, it gives us a deeper way of seeing the night sky. Not as an isolated dome of stars, but as a fragile, luminous layer sustained by a hidden partner. The night sky has always been beautiful. Now we know it's also mysterious, resting on the shoulders of a companion that's been there all along. We find ourselves back beneath the quiet of the night sky. We've wandered through galaxies and halos, traced the invisible web that stretches across the cosmos, followed the clues of a universe where most of what exists is hidden. We've learned that stars aren't the whole, that the visible is only a small fraction, and that dark matter and dark energy, silent, unseen, carry the weight of reality. But this isn't an ending. The mystery remains. The search continues, in the silence of underground laboratories, in the roar of colliders, in the steady gaze of telescopes watching the sky. The universe still keeps its secrets, and we're still learning how to listen. That's not reason for frustration. It's an invitation. There's always more to discover, always another layer beyond what we see. As you rest now, let that be a comfort. Mystery isn't absence, it's presence. It means the universe is alive with possibility, larger than our understanding, deeper than our imagination. To close your eyes beneath that truth is to know that you're part of something vast, supported by what you cannot see, connected to a story still unfolding. The galaxies will continue to turn. The halos will continue to hold. The universe will continue to expand. The night sky has its secret companion, and so do you.